What if everything we think we know about the universe is built on a fundamental misunderstanding? What if the very fabric of space and time, the stage upon which all of existence plays out, is not the smooth, predictable continuum we believe it to be, but is instead riddled with glitches, tears, and phenomena so bizarre they defy the very laws of physics as we've written them? This isn't the plot of a science fiction novel. This is the frontier of modern cosmology, a place where the map of reality is being redrawn by the discoveries we're making every single day. We are living in a golden age of cosmic detective work, where each new observation from powerful telescopes and deep space probes has the potential to unravel our most cherished scientific theories and introduce us to a universe far stranger and more wonderful than we ever imagined. Welcome, cosmic detectives. Today we're embarking on a journey to the very edges of understanding to explore 25 of the most perplexing, mind-bending anomalies in space-time. These are not just simple mysteries. These are cosmic paradoxes that have left the world's brightest physicists scratching their heads, phenomena that suggest our reality might be a kind of cosmic simulation, or that multiple universes are bubbling just beyond our perception, or that gravity itself operates in ways we have yet to comprehend. We'll be investigating gravitational anomalies that warp the cosmos in impossible ways, particles that seem to communicate instantaneously across vast distances, and regions of space where time itself appears to behave erratically. Each one of these enigmas is a piece of a puzzle, a clue left behind by the universe, challenging us to think bigger and dig deeper. So if you've ever looked up at the night sky and felt a sense of profound wonder, if you've ever questioned the nature of your own reality, then you are in the right place. This is your invitation to join the investigation, to pull back the curtain on the greatest show in the cosmos. We're about to dive into a collection of cosmic curiosities that will stretch your imagination, challenge your perception, and perhaps even change the way you see the universe and your place within it. Forget what you think you know, open your mind to the impossible, and let's begin our countdown of the 25 most unexplained anomalies in space-time. Our journey into the cosmic unknown begins not in the distant depths of interstellar space, but much closer to home, with a pair of robotic pioneers that first exposed a crack in our understanding of gravity. The Pioneer 10 and 11 spacecraft, launched in the early 1970s, were marvels of human engineering, tasked with the first ever flybys of Jupiter and Saturn before embarking on an endless journey into the void. For decades, scientists meticulously tracked their paths, expecting their trajectories to be governed solely by the predictable tug of the sun's gravity and the gentle nudge of solar radiation. But something was wrong. As the twin probes ventured beyond the orbit of Pluto, deep space navigation data revealed a tiny, relentless, and utterly unexplained force acting upon them. Each year they were falling about 500 kilometers behind their projected positions. It was as if an invisible hand was gently, but persistently, applying the brakes. This was the Pioneer anomaly. For over 30 years, this minuscule discrepancy, a deceleration equivalent to just 1/10,000,000th of the gravity we feel on Earth, became a monumental puzzle. At first, many suspected a simple engineering explanation, perhaps the subtle push of heat radiating unevenly from the spacecraft's nuclear power sources. But as the data piled up and every conventional explanation was tested and found wanting, the anomaly forced physicists to consider far more radical ideas. What if our model of gravity, Isaac Newton's and later Einstein's equations that have guided our understanding of the cosmos for centuries, was subtly incorrect over vast distances? Could this be the first observational evidence for modified gravity, a new physical law that only manifests itself in the weak gravitational fields of deep space? The implications were staggering, suggesting that the entire cosmic dance of galaxies and the expansion of the universe itself might need to be reevaluated through a new gravitational lens. Ultimately, after a Herculean effort that involved recovering decades-old data and building new computer models, the most widely accepted explanation turned out to be the more mundane one. The anisotropic or uneven thermal radiation from the spacecraft's own electronics and power systems was indeed providing the tiny thrust needed to explain the drift. Yet the ghost of the Pioneer anomaly lingers. It stands as a powerful testament to the importance of precision and a humbling reminder that even the smallest, most persistent signal, when it defies explanation, can force us to question the very foundations of our reality. It was our first major lesson in modern cosmology that the universe often speaks in whispers, not shouts. Yet as we solved one deep space riddle, another equally perplexing mystery was emerging much closer to Earth, hidden in the high-stakes orbital ballet of interplanetary spacecraft. When scientists send a probe on a multi-billion-mile journey to the outer solar system, they don't just point it at a planet and fire the engines. Instead, they use a clever technique called a gravity assist, using a planet's own gravitational pull as a slingshot to fling a spacecraft on its way, saving immense amounts of fuel and time. The mathematics for these flybys are exquisitely precise, a dance of orbital mechanics perfected over decades, but during a series of Earth flybys, this celestial dance developed a strange and consistent hiccup. As spacecraft like NASA Galileo probes swung by our planet to gain momentum for its trip to Jupiter, something unexpected happened. Instead of following its predicted path with perfect accuracy, Galileo experienced a tiny, inexplicable increase in its velocity. It was as if the spacecraft had received an unseen extra push. This became known as the flyby anomaly, and it wasn't a one-time fluke. The European Space Agency's Rosetta comet chaser, on its long voyage, performed not one, but two Earth flybys. On both occasions, in March 2005 and November 2007, precise Doppler tracking data recorded a velocity jump that defied all conventional calculations. The numbers were small, a change of just a few millimeters per second, but in the world of orbital dynamics, where a mistake of a single centimeter per second can mean missing a target by thousands of miles over a multi-year journey, this was a major problem. The energy gain was real, measurable, and completely unaccounted for in our models of gravity and planetary motion. It was a ghost in the machine of celestial navigation. So what could be giving these spacecraft this unplanned boost? The leading hypotheses are as fascinating as the anomaly itself. One compelling idea points toward a phenomenon known as rotational frame dragging, a subtle effect predicted by Einstein's theory of general relativity. The theory suggests that a massive rotating object like Earth doesn't just warp the space around it, it also draggles the very fabric of space-time along with it as it spins, like a spinning ball submerged in a thick fluid. Perhaps this dragged space-time imparts a minuscule amount of extra momentum to a passing spacecraft. While the math suggests the effect would be incredibly small, some physicists wonder if our current models are underestimating its influence during a close planetary flyby. Another more exotic theory ventures into the realm of the invisible. What if the spacecraft are passing through localized clouds of dark matter gravitationally bound to Earth? If our planet is surrounded by a faint halo of this mysterious, unseen substance, a spacecraft dipping through it could experience a slight additional gravitational tug, manifesting as a small speed increase. While this is highly speculative, the very fact that such a profound idea is even on the table shows just how baffling this anomaly truly is. Despite decades of data and analysis, no single explanation has yet gained universal acceptance. The flyby anomaly remains an open case, a tiny but persistent whisper from the universe that even here, in our own cosmic backyard, the final word on gravity has not yet been written. But our exploration of cosmic mysteries doesn't end with the mechanics of moving through space. It extends to the very blueprint of the universe itself, a blueprint we can read in the faint, cold glow of its birth. To uncover our next anomaly, we must peer back in time to a mere 380,000 years after the Big Bang. The entire cosmos was a searing, opaque plasma soup, too hot for light to travel freely. Then, in an event known as recombination, the universe cooled just enough for atoms to form, allowing light to burst forth and travel across the cosmos for the very first time. That first light is still all around us today, stretched and cooled by the universe's relentless expansion into a uniform microwave static that bathes the entire sky. This is the cosmic microwave background, or CMB, and it is the oldest fossil in existence. For decades, the CMB has been the cornerstone of modern cosmology. Detailed maps, most famously from the Planck satellite, show it to be incredibly uniform with tiny random fluctuations in temperature, warmer spots and cooler spots that represent the seeds from which all galaxies, stars, and planets would eventually grow. This overall uniformity perfectly supports the cosmological principle. a foundational idea stating that on the largest scales, the universe is homogeneous and isotropic. In simple terms, it should look the same in every direction with no preferred center, no special axis, and no up or down. There should be no grand cosmic fingerprint smudging the map of creation. But that is precisely what some scientists believe they have found, an anomaly so unnerving they've given it a dramatic name, the axis of evil. When researchers analyze the intricate patterns in the SIMB, they apply powerful statistical tools to see if the hot and cold spots are truly random, as inflation theory predicts. To their astonishment, they discover that the largest scale fluctuations are not completely random. Instead, they appear to be aligned along a particular axis that stretches across the sky, a preferred direction that seems to split the universe in two. Even more bizarrely, this so-called axis appears to be curiously aligned with our own solar system's plane, the ecliptic. This is deeply unsettling. It's as if the architecture of the entire cosmos has a subtle, hidden arrow pointing in a specific direction, and that direction just happens to coincide with our own insignificant little corner of the universe. The probability of this happening by pure chance is incredibly low, leading to the statistical significance that makes this more than just a curiosity. The implications of this are profound, striking at the very heart of our understanding of reality. If the axis of evil is real and not an illusion, it would violate the cosmological principle. The universe would not be the same in every direction after all. It would have a large-scale structure, a preferred orientation that would force us to abandon one of our most cherished assumptions about the cosmos. This in turn creates serious problems for the theory of cosmic inflation, the leading idea for the universe's explosive initial growth. Inflation was designed specifically to produce a universe that is smooth and isotropic on large scales. The presence of a giant cosmic axis would mean our best theory of the Big Bang is fundamentally incomplete, or perhaps even wrong. Naturally, such a radical claim has sparked intense debate. Skeptics argue that the anomaly could be a statistical fluke, a classic case of pareidolia, the human tendency to see patterns in random noise, like seeing a face in the clouds. They suggest that our methods for analyzing the SIMB data might inadvertently introduce this alignment, or that we are simply being misled by foreground contamination from our own Milky Way galaxy, which we have to subtract from the maps. The evil in the axis of evil, they say, might just be our own human bias, our desire to find meaning and order where none exists, yet the signal persists. With each new, more precise map of the SIMB, scientists check to see if the axis will disappear, but it stubbornly remains. This ongoing debate is a beautiful example of the scientific process at work, a tense and thrilling standoff between a foundational principle and an inconvenient piece of data. Is the axis of evil a true feature of the universe, a cosmic signpost pointing toward a deeper layer of reality we have yet to understand? Or is it the ultimate cosmic coincidence, a trick of statistics that has fooled us into thinking we are special? For now, this ancient globe from the dawn of time holds its secret close, leaving us with a universe that may be far less random and far more strangely ordered than we ever dared to believe. If the axis of evil suggests our universe might have a hidden architecture, then our next cosmic mystery reveals that this entire structure might be in motion, pulled by a force from a realm we cannot see. Astronomers have long understood that the universe is expanding, with galaxies generally rushing away from each other as the fabric of space-time stretches. Yet when they began to meticulously map the motion of enormous galaxy clusters using the hot gas that surrounds them, they detected something profoundly strange. These colossal structures, each containing thousands of galaxies, were not just moving with the general flow of cosmic expansion. Instead, a significant number of them appeared to be streaming in a coherent direction, as if pulled by a vast, unseen tide. This mysterious collective motion has been dubbed dark flow. The existence of dark flow is one of the most controversial claims in modern cosmology. The observed velocities are immense, hundreds of kilometers per second, and they persist across billions of light years. What makes this so baffling is that, according to our standard model, there shouldn't be anything large enough on the other side of the cosmic horizon to generate such a pull. The gravitational influence of all the known matter in our observable universe simply cannot account for it. This has led to a truly mind-bending hypothesis. the source of dark flow may lie beyond the visible edge of our cosmos. It could be the gravitational tug of a massive, unseen structure in a neighboring region of space-time, another universe entirely, or a vastly different patch of our own greater multiverse, exerting its influence from a place we can never hope to observe directly. It's a ghostly current flowing through the cosmic ocean, and we are only just beginning to sense its pull. While dark flow hints at influences from beyond our cosmic horizon, a separate and equally powerful gravitational mystery is at work much closer to home, on a scale that still defies comprehension. Our Milky Way galaxy is not floating motionless in space. It, along with our entire local group of galaxies, is racing through the cosmos at a staggering 2 million kilometers per hour. For decades, astronomers traced the source of this motion back to a region of space in the general direction of the Centaurus constellation, a mysterious and immense gravitational focal point they named the Great Attractor. This colossal anomaly, with a mass equivalent to tens of thousands of Milky Way galaxies, acts like a cosmic whirlpool, drawing everything in our intergalactic neighborhood toward it. The search to identify the Great Attractor, however, hit a major obstacle: our own galaxy. From our vantage point within the dusty, star-filled disk of the Milky Way, the precise center of this gravitational pull is hidden from view, located in what astronomers call the zone of avoidance. It's like trying to see a distant city while standing in a dense fog bank. For years, the true nature of the Great Attractor remained shrouded in this cosmic secrecy, leading to speculation about what unimaginable concentration of mass could possibly be causing such a vast motion. The breakthrough came with new technologies and telescopes capable of peering through the galactic clutter using infrared and radio wavelengths. What they found was not a single monstrous object, but something even more grand. The Great Attractor is not the ultimate destination, it is merely a waypoint. Our entire local flow of galaxies, pulled by the Great Attractor, is itself part of a much larger river of motion, all streaming toward an infinitely more massive structure known as the Shapley supercluster. This is one of the largest known conglomerations of matter in the entire observable universe, a dense knot containing tens of thousands of galaxies. The gravitational dominance of Shapley is so immense that it effectively rules the dynamics of our entire cosmic neighborhood. Yet, even with this discovery, the story isn't fully complete. The combined gravity of the Great Attractor and the Shapley supercluster still doesn't perfectly account for the full velocity of our motion. This discrepancy keeps the door open for other, even more distant and massive structures to be influencing us, or for the lingering, controversial possibility that a component of dark flow is also contributing to our journey. Together, dark flow and the Great Attractor paint a humbling picture. We are not merely expanding outward in a uniform universe, but are instead caught in a complex cosmic web of gravitational currents, pulled by hidden masters both within our observable realm and perhaps from realms that lie forever beyond our sight. From the grand cosmic currents that pull entire clusters of galaxies, we now turn our gaze inward to the mysteries lurking within our own solar system, a place we often assume we know well, but which continues to reveal its own startling secrets. Our next set of anomalies begins at the frozen frontier of our planetary neighborhood, with a puzzling void that astronomers call the Kuiper Cliff. Far beyond the orbit of Neptune, stretching from about 30 to 55 astronomical units from the Sun, lies the Kuiper Belt, a vast disk of icy debris left over from the solar system's formation. Think of it as a far more distant and expansive cousin to the asteroid belt, home to dwarf planets like Pluto and countless frozen planetesimals. As we survey this region, we expect the number of objects to gradually decrease the farther out we look as the primordial material thins out. But that's not what happens. Instead, at approximately 50 astronomical units, the population of Kuiper Belt objects drops off a cliff. It's an abrupt and dramatic boundary, as if someone built a wall at the edge of the solar system. This Kuiper Cliff presents a major puzzle. Our models of solar system formation suggest the disk should extend much farther, perhaps out to hundreds of astronomical units, with a smooth tapering off of objects. The sheer suddenness of this drop defies easy explanation and has sparked compelling theories. The most tantalizing possibility is that the cliff is the gravitational signature of an unseen world, a hypothetical planet 9. The idea is that a massive, yet-to-be-discovered planet, several times the size of Earth, could be orbiting in the distant blackness. Its gravitational influence would have sculpted this region, either clearing out objects or herding them into orbits that make them difficult for us to detect from our vantage point. While the search for this elusive planet continues, other scientists propose that the cliff is simply the original outer edge of our protoplanetary disk, a fossilized boundary from the solar system's birth, or that the objects beyond are too small and dark for our current telescopes to see. Yet the abruptness remains a challenge, leaving the Kuiper Cliff as a stark reminder that we have not yet finished mapping our own cosmic backyard. While the Kuiper Cliff questions the structure of our solar system, another profound anomaly challenges our understanding of our own planet's history and the very star that gives us life. This is the faint young sun paradox. We know from stellar physics that stars like our sun grow steadily brighter as they age. Billions of years ago, when life first emerged on Earth, our sun was only about 70% as luminous as it is today. According to all our climate models, that weaker sun should not have provided enough heat to keep the early Earth from being a global, frozen snowball. The calculations are clear. With that faint young sun, Earth's oceans should have been permanently locked in ice. Yet the geological record tells a completely different story. Ancient rocks show clear evidence of liquid water and even life, stretching back more than 3.5 billion years. The early Earth was not an icy wasteland. It was surprisingly warm and hospitable. So what was keeping the planet warm? This paradox forces us to consider that Earth's early atmosphere must have been a very different and much more potent blanket. The leading hypothesis points to a high concentration of greenhouse gases like methane and carbon dioxide, which would have trapped far more of the sun's feeble heat. Another fascinating possibility involves ammonia, another powerful greenhouse gas, or perhaps a complete lack of biological organisms that could draw down carbon dioxide from the air. Some more speculative ideas even suggest a different planetary albedo, with less cloud cover or darker land surfaces absorbing more heat. Solving this paradox is not just an academic exercise, it is crucial for understanding the delicate balance that makes a planet habitable and has profound implications for our search for life on distant exoplanets. It tells us that a planet's climate is a complex interplay of stellar output, atmospheric composition, and biological activity, a system that can find ways to sustain warmth even under a faint young sun. From an ancient Earth warmed by a mysterious greenhouse, our final solar system anomaly brings us to a visitor from a realm far beyond our own, an object that defied categorization and sparked a scientific debate that continues to this day. In October 2017, astronomers in Hawaii detected an object hurtling through our solar system at high speed. Its trajectory was immediately recognized as hyperbolic, meaning it was not bound by the sun's gravity. It was a visitor from interstellar space. They named it Oumuamua, Hawaiian for a messenger from afar arriving first. Its arrival was momentous, the first confirmed object from another star system. But as scientists raced to observe it, Oumuamua revealed a series of bizarre properties. It was tumbling chaotically, and its shape was wildly elongated, perhaps 10 times as long as it was wide, resembling nothing we have in our own solar system. Most baffling of all, as it traveled away from the sun, it exhibited a slight but definite non-gravitational acceleration. It was speeding up in a way that could not be explained by the gravitational pull of the sun or planets alone. This unexpected acceleration launched a firestorm of speculation. What was pushing it? The immediate suspicion was outgassing, the same process that powers comets, where frozen ices on the surface heat up and turn to gas, jetting away and providing a small thrust. But Oumuamua showed no visible coma, no cloud of gas and dust that all comets display when they outgas. It appeared as a silent, barren rock. This missing coma is the core of the mystery. One compelling theory suggests Oumuamua was a comet after all, but one made primarily of nitrogen ice. As it passed close to the sun, the nitrogen would have sublimated, providing the thrust without creating a dusty coma that our telescopes could easily detect. Another proposal is that it was a hydrogen iceberg, a chunk of solid hydrogen that would similarly vent invisible hydrogen gas. Both of these exotic compositions point to Oumuamua forming in a very different kind of planetary system than our own. Of course, the most sensational hypothesis came from Harvard astronomer Avi Loeb, who famously raised the possibility that Oumuamua could be an artificial artifact, like a light sail propelled by radiation pressure from starlight. While this idea captured the public imagination, the vast majority of the scientific community favors natural explanations, arguing that we should exhaust all possibilities within known physics before leaping to such extraordinary conclusions. Yet the very fact that the debate persists highlights a fundamental truth. Oumuamua was a sample of the vast, unexplored galaxy, and its strange properties are a preview of the diversity of objects that must exist between the stars. It was a one-of-a-kind data point, a messenger that passed through our system too quickly for us to fully decipher, leaving behind a trail of accelerated questions about what else might be sailing through the dark, silent spaces between the stars. Leaving behind the enigmatic interstellar traveler Oumuamua, we now turn our attention to a mystery that came not from the dark depths of space, but from the silent airwaves themselves, a single powerful burst of radio energy that for one fleeting moment seemed to scream, "We are here." This is the story of the WOW signal, an event so startling and so perfectly strange that the astronomer who discovered it was moved to scribble the now famous exclamation on a computer printout, giving this cosmic enigma its unforgettable name. It was a quiet Sunday evening on August 15, 1977, at Ohio State University's Big Ear radio telescope. This massive instrument was part of the long-running search for extraterrestrial intelligence, or SETI, program, systematically scanning the sky for any signal that stood out from the natural background radio hiss of the universe. The system worked automatically, and the data was printed out on long, continuous sheets of paper for astronomers to review later. It was during this routine check a few days later that volunteer Jerry Amon, painstakingly going through the columns of alphanumeric characters, saw something that made his heart stop. There in the data from a scan of the constellation Sagittarius was a vertical column of characters so intense that Amon circled it in red pen and in the margin simply wrote, "Wow." The signal had been detected on a frequency of 1420 megahertz, a radio band that is internationally protected for astronomical research because it is one of the main emission lines of neutral hydrogen, the most common element in the universe. The thinking was that any intelligent civilization wanting to announce its presence would logically use this universal, fundamental frequency, a cosmic hailing channel. What made the signal so extraordinary was its intensity and its structure. The Big Ear telescope listened to a single point in the sky for 72 seconds as the Earth's rotation carried the target through its view. The signal appeared suddenly, rose to a stunning peak of intensity, and then faded away exactly as expected, creating a perfect bell curve on the printout. The alphanumeric string 6EQUJ5 was actually a code for the signal's strength, with numbers 1 through 9 and then letters from A to Z representing progressively stronger values. The U in the sequence was a reading 30 times stronger than the background noise, an intensity the telescope had never recorded before and has never recorded since. It was a narrowband signal, meaning it was concentrated on one specific frequency, which is a hallmark of an artificial transmitter. Natural cosmic objects typically emit a broad, messy smear of radio waves. For 72 seconds, the Big Ear telescope listened to what seemed to be a perfect candidate for a message from another star, and then it was gone. The immediate and obvious next step was to listen again. The region of space where the signal originated, near a star cluster known as Chi Sagittarii, became the most intensely studied patch of sky in the history of SETI. Astronomers pointed the Big Ear and countless other powerful radio telescopes back to that exact spot again and again for decades. They scanned not just the original frequency, but a wide range of bands around it. The result was a profound and enduring silence. The WOW signal was never heard again. This one time, only nature is central to the mystery. If it was a deliberate transmission from an extraterrestrial civilization, why did it stop? Was it a targeted beacon that swept past our solar system, never to return, or was it a one-off event, a catastrophic explosion, or a momentary burst of activity that we happened to catch by pure cosmic luck? In the absence of a repeat performance, scientists have worked to find a natural, terrestrial explanation. The signal was intermittent, which rules out a continuous source like a satellite or a ground-based transmitter. It wasn't an aircraft or a passing spy plane, as its duration and frequency profile don't match. One of the more compelling natural explanations emerged in 2016 when a team of researchers proposed that the signal could have been caused by a cloud of hydrogen gas surrounding a passing comet. Two comets, in fact, were in the approximate area of the sky at that very time. The idea is that the sun's radiation could cause such a hydrogen cloud to emit a strong, narrowband signal at the 1420 megahertz frequency. It's a clever and plausible hypothesis. However, upon closer inspection, this theory has significant problems. The comets in question were not actually in the exact beam of the telescope at the time of the detection, and critics point out that cometary hydrogen clouds are generally too diffuse to produce a signal of such incredible focus power. While a natural explanation is always the most scientifically parsimonious path, the comet hypothesis has, for many, failed to fully extinguish the intrigue. This leaves us with a profound and lingering question, a mystery that has captivated astronomers and the public for nearly half a century. The WOW signal remains the single best candidate for potential extraterrestrial transmission in the history of SETI, a beacon of possibility in the vast, quiet cosmos. It stands as a testament to both the promise and the profound challenge of the search for other intelligent life. The universe is immense, and our window of listening is infinitesimally small. We might have heard a civilization's message for just 72 seconds, a cosmic phone that rang once and then went silent forever. Whether it was a natural phenomenon we don't yet fully understand or a genuine hello from the void, the WOW signal continues to be a powerful symbol of our own yearning to know if, somewhere in the great dark ocean of space, there's another island of consciousness looking back at us. Just as the WOW signal presented a fleeting mystery from the cosmos, our next anomaly represents a permanent, fundamental problem etched into the very motion of the galaxies themselves. It's a puzzle that doesn't vanish when we look harder. It only deepens, forcing us to confront the possibility that most of the universe is made of something we cannot see. This is the mystery of the galaxy rotation curves, and it's the single strongest piece of evidence we have for the existence of dark matter. To understand the problem, picture a spiral galaxy like our own Milky Way, a vast spinning pinwheel of stars, gas, and dust. According to the well-tested laws of gravity, primarily governed by Newtonian physics on these scales, the speed at which stars orbit the galactic center should follow a predictable pattern. Think of our own solar system. The planets closer to the Sun, like Mercury and Venus, orbit at tremendous speeds, while the outer planets, like Jupiter and Saturn, move much more slowly. This is because the Sun's gravitational grip weakens with distance. We would expect the same to be true in a galaxy where the vast majority of the visible mass, all the stars and glowing gas we can see, is concentrated in the bright central bulge. Stars near the outer edges of the galactic disk, far from this central mass, should be dragging their feet, orbiting at much slower velocities than those closer in. But when astronomers in the mid-20th century began to measure these rotation speeds using the Doppler shift of radio waves from hydrogen gas, they found something astonishing and completely counter to this prediction. The stars and gas in the outer reaches of galaxies were not moving slowly at all. In fact, they were whipping around the galactic center at speeds just as high as the stars much closer in. The rotation curve, the graph plotting orbital speed against distance from the center, didn't show the expected dramatic drop-off. Instead, it remained flat far out into the galactic hinterlands. This was a direct and glaring violation of Newtonian gravity based on the visible mass alone. For the outer stars to be moving that fast without being flung off into intergalactic space, there had to be an immense amount of additional, unseen matter providing extra gravitational glue, holding the entire structure together. The person who placed this anomaly on rock-solid observational footing was the brilliant astronomer Vera Rubin, working with Kent Ford in the 1970s and 80s. By meticulously measuring the rotation curves of dozens of spiral galaxies, Rubin and her team demonstrated that this flat rotation curve wasn't a rare fluke, it was a universal feature. Everywhere they looked, galaxies were rotating in a way that defied the gravity of their visible components. Her work transformed dark matter from a speculative curiosity into a central problem of modern physics. It became clear that galaxies are not just what we see, they are embedded within enormous, massive halos of something invisible, halos that extend far beyond the visible starlight. This hidden mass outweighs the ordinary, visible matter by a factor of about 5 to 1, meaning that over 80% of the matter in the universe is completely invisible to our telescopes. So what is this mysterious dark matter? For decades, the leading candidates have been hypothetical particles known as WIMP, or weakly interacting massive particles. These are theorized to be heavy, sluggish particles that don't interact with light or ordinary matter except through gravity and possibly the weak nuclear force. They would be relics from the Big Bang, streaming through the universe and through our very bodies by the billions every second, completely unnoticed. Vast experiments deep underground, shielded from cosmic rays, have been searching for the rare telltale recoil of a WIMP colliding with an atomic nucleus, but so far, they've come up empty. This lack of a direct detection has allowed other candidates to gain prominence. One particularly compelling alternative is the action, a particle that was originally proposed to solve a different problem in particle physics. Actions would be incredibly light, almost ghost-like particles that could collectively make up the dark matter. Their search is also underway in sophisticated laboratory experiments that look for them converting into photons in the presence of strong magnetic fields. The persistent failure to directly detect any of these particles has led some physicists to propose a radically different solution. What if there is no dark matter at all? What if our understanding of gravity itself is wrong? This is the premise of modified Newtonian dynamics, or MIND. First proposed by physicist Mordechai Milgrom in the 1980s, MIND suggests that Newton's laws of motion need a slight tweak at very low accelerations, like those experienced in the extreme outskirts of galaxies. In this regime, gravity will become slightly stronger than Newton predicts, providing the extra pull needed to keep fast-moving outer stars in their orbits without invoking any unseen matter. The appeal of MIND is its elegant simplicity. It accounts for the flat rotation curves remarkably well without requiring a whole new form of matter that we can't find. However, MIND faces its own monumental challenges. While it works beautifully for explaining the rotation of individual galaxies, it struggles to account for other lines of evidence that also point to dark matter's existence. For instance, observations of the Bullet Cluster, two colliding galaxy clusters, provide what many consider a knockout blow for MIND. When these clusters collided, their visible hot gas clouds slammed into each other and slowed down, but the majority of their mass, inferred through gravitational lensing, sailed right through the collision and ended up in a different location than the gas. This is exactly what you'd expect if the mass were made of dark matter particles that don't interact with each other or with the gas. It's very difficult for a modification of gravity to explain how the gravity of a cluster could become separated from its visible matter. Similarly, the precise patterns in the cosmic microwave background, the afterglow of the Big Bang, are exquisitely fit by models that include dark matter, while MIND-based models have a much harder time replicating the data. So we are left with a grand stalemate. On one side, we have the dark matter hypothesis, which is incredibly successful at explaining the universe on the largest scales, but is frustratingly elusive in the lab. On the other, we have MIND, which elegantly solves the specific problem it was designed for, but fails to provide a complete universal theory of gravity that works across all cosmic phenomena. This isn't just an academic debate, it's a fundamental schism in our understanding of physics. The mystery of the galaxy rotation curves, first so clearly mapped by Vera Rubin, has opened a chasm in our knowledge, forcing us to choose between the existence of a vast, hidden cosmos of unknown particles or a rewrite of the gravitational laws that have guided science for centuries. It remains one of the most profound and consequential puzzles in all of science. Moving from the hidden gravitational scaffolding of dark matter, we encounter a cosmic rift that cuts right to the heart of our understanding of the universe's ultimate fate, a disagreement so fundamental it's known as the Hubble tension. At its core, this is a dispute over a single critical number, the Hubble constant, which measures the current expansion rate of the universe. For decades, astronomers have been striving to pin down this number with ever greater precision, expecting that different, reliable methods would eventually converge on a single, agreed-upon value. Instead, as our tools have become more sophisticated, the results have dramatically split into two irreconcilable camps, creating a modern crisis in cosmology. One approach, often called the early universe method, uses the cosmic microwave background as its ultimate ruler. By analyzing the exquisite, detailed snapshots from the Planck satellite, scientists can work backwards from the conditions of the infant cosmos to predict how fast the universe should be expanding today. This is a powerful, self-consistent method based on our well-tested standard model of cosmology, lambda CDM. It gives us a Hubble constant of about 67 kilometers per second per megaparsec. In simpler terms, this means that for every megaparsec, a distance of about 3.3 million light years, a galaxy is moving away from us 67 kilometers per second faster. This early universe measurement is incredibly precise with a margin of error of less than 1%. The competing method looks at the late universe, the cosmos as it exists right now. Here, astronomers use a cosmic distance ladder to measure expansion directly. The first rungs of this ladder are Cepheid variable stars, which pulsate at a rate directly related to their true brightness. By measuring their pulsation period from Earth, astronomers can determine their intrinsic luminosity, and by comparing that to how dim they appear in the sky, they can calculate their distance with remarkable accuracy. These Cepheids are then used to calibrate the next rung of the ladder, which includes Type Ia supernova. These stellar explosions are so brilliant and uniform that they act as standard candles, allowing us to gauge distances to galaxies far across the cosmos. By observing how fast these distant galaxies are receding from us their redshift, and plotting that against their independently measured distances, we get a direct readout of the Hubble constant. The result from this late universe technique consistently points to a faster expansion rate, around 73 kilometers per second per megaparsec. The disagreement between 67 and 73 might seem small, but in the world of high-precision cosmology, it's a glaring chasm. The statistical significance of this gap is now greater than 5 sigma, which is the gold standard in physics for claiming a genuine discovery. This isn't a case of sloppy measurements, it's a robust signal that something is fundamentally wrong. Either one of our methods contains a hidden, systematic error we haven't yet identified, or our standard model of the universe is incomplete. The first possibility has been investigated exhaustively. Could there be an unknown flaw in how we measure Cepheid distances? Perhaps our understanding of the supernova themselves has a subtle bias. Teams have checked and rechecked the data, and while tiny adjustments can be made, the tension stubbornly refuses to go away. It appears to be real. This leads us to the far more exciting possibility that the Hubble tension is a direct pointer to new physics. If the discrepancy is real, it means that the universe today is expanding faster than our model, based on its initial conditions, predicts it should be. What unknown force could be giving cosmic expansion this extra kick? One compelling idea involves dark energy, the mysterious component driving the acceleration of the universe. What if dark energy isn't constant, as in Einstein's cosmological constant, but is dynamic, a hypothetical form of evolving dark energy, sometimes called early dark energy, could have briefly injected extra energy into the universe in its first few 100,000 years, subtly changing the initial conditions from which we extrapolate forward. This would throw off the Planck measurement, making it predict a slower modern expansion than is actually occurring. Other theories are even more exotic. Could there be a new type of relativistic particle streaming through the cosmos from the Big Bang that we haven't accounted for? These particles would affect how quickly structures form in the early universe, again tweaking the starting point of our cosmic calculations. Or perhaps dark matter itself has properties we don't understand. Maybe it can interact with itself or with dark energy in ways that subtly alter the expansion history. The most mind-bending proposals even suggest that the Hubble tension is a sign that the density of matter in the universe is not uniform, and that we live in a local void, a vast underdense region of space, which is making our local measurements of expansion unrepresentative of the cosmos as a whole. The implications of solving this puzzle are nothing short of revolutionary. Confirming that the Hubble tension requires new physics would be akin to the moment when the anomalous orbit of Mercury revealed the flaws in Newtonian gravity and paved the way for Einstein's general relativity. It would force us to rewrite the standard model of cosmology, introducing new components or new forces that have shaped the evolution of everything we see. This isn't just an academic debate over a number. It's a struggle to correctly narrate the story of the universe from its first fleeting moments to its ultimate, far future destiny. The Hubble tension is the universe presenting us with a glaring inconsistency in our own textbook, a clear signal that there are profound chapters of cosmic history still waiting to be discovered. If the Hubble tension reveals a crack in our cosmic timeline, then the mystery we turn to now exposes a fundamental flaw in the very recipe of the cosmos itself. We are made of stardust, as the famous saying goes, forged in the nuclear furnaces of generations of stars, but the very first elements, the most primordial ingredients, were cooked up in the very first minutes after the Big Bang, in a frenetic period known as Big Bang nucleosynthesis. For the most part, our models of this cosmic cookbook are spectacularly successful. The predicted amounts of hydrogen and helium that emerge from this primordial fireball match what we observe in the oldest stars and gas clouds almost perfectly. There is, however, one stubborn, glaring exception, a single ingredient that just doesn't measure up: lithium. This is the long-standing lithium problem, and it represents a deficit so precise and so persistent that it challenges our understanding of the universe's first nuclear reactions. To appreciate the depth of this problem, we need to travel back to a time when the entire universe was less than 20 minutes old. In those first few seconds, the cosmos was an unimaginably dense and hot soup of fundamental particles. As it expanded and cooled, protons and neutrons began to fuse, building the first atomic nuclei. The process was a frantic, high-speed dance of nuclear interactions, creating deuterium, then helium, and trace amounts of a few other light elements. According to our most sophisticated models, which incorporate our well-measured rates of nuclear reactions, a specific quantity of the lithium-7 isotope should have been synthesized during this brief window and then frozen into the cosmic fabric as the universe continued to cool and expand. The calculations are precise, and they predict that the oldest stars in our galaxy, which form from this pristine, unmixed gas, should show a specific abundance of lithium in their atmospheres. Yet when astronomers point their telescopes at these ancient stellar fossils, the numbers don't match. The observed amount of lithium-7 in these old stars is only about 1/3 of what the theory says it should be. We are not talking about a vague discrepancy. This is a factor of 3 shortfall, a glaring mismatch that has withstood decades of scrutiny and improved observations. It's as if we followed a cosmic recipe to the letter, but the cake consistently comes out missing a key ingredient. This isn't a minor quibble. It's a direct challenge to our understanding of nuclear physics in the universe's first moments. If our model of Big Bang nucleosynthesis is wrong about lithium, what else might it be subtly miscalculating? The quest for a solution has led physicists down several fascinating paths. The most straightforward possibility is that our knowledge of the nuclear physics involved is incomplete. The primordial production of lithium-7 depends on a complex chain of reactions, and its eventual destruction can be influenced by other nuclear pathways. Perhaps there is a previously unknown nuclear resonance, a sort of shortcut in the reaction, that would have destroyed lithium-7 more efficiently in the early universe. Alternatively, maybe the cross-sections, which measure the probability of these nuclear reactions occurring, have small errors that become magnified in the unique conditions of the Big Bang. Laboratories around the world have worked to remeasure these nuclear rates with incredible precision, but so far, no revision has been large enough to fully resolve the threefold gap. This persistent failure of conventional nuclear physics has opened the door to more exotic explanations, many of which point to new particles beyond the standard model. One compelling idea involves a hypothetical particle known as the action. If actions existed in the early universe, they could have altered the balance between protons and neutrons during nucleosynthesis, subtly changing the initial conditions for building elements and ultimately leading to less lithium being produced. Another radical proposal involves a type of supersymmetric particle, often called a gravitino or a neutralino. If such a particle were unstable, it could have decayed during or just after Big Bang nucleosynthesis, injecting high-energy photons into the primordial soup. These photons could have then broken apart the delicate deuterium and helium nuclei that were the building blocks for lithium-7, effectively dismantling it before it could accumulate. Yet another layer of complexity arises from the observations themselves. Could the problem lie not in the early universe, but in the ancient stars we use as cosmic probes? Astronomers measure the primordial lithium abundance by studying the atmospheres of the most ancient stars in the Milky Way's halo, known as population Roman II stars. The strength of the absorption line for lithium in their spectra tells us how much of the element is present. But what if these stars are not pristine containers? Over their billions of years of life, could they have somehow destroyed or diluted the lithium in their surface layers? Stars are known to have circulation patterns that can drag surface material down into the hot interior, where temperatures are high enough to burn lithium. If this mixing is more efficient than we currently model, it could explain why we see less lithium today than was originally present. However, constructing stellar models that destroy exactly the right amount of lithium without contradicting other observations has proven to be a tremendous challenge. The lithium problem therefore stands as a magnificent stalemate. On one side, we have the impeccable success of Big Bang nucleosynthesis in predicting the cosmic abundances of hydrogen and helium, a triumph that gives us great confidence in the overall picture. On the other, we have this one persistent anomaly with lithium that refuses to go away. It forces us to consider that our understanding of the universe's first few minutes is still incomplete. Whether the solution lies in a subtle refinement of nuclear physics, the discovery of a new fundamental particle, or a better understanding of stellar astrophysics, resolving the lithium problem would not just plug a hole in a theory, it would open a new window into the physics of the primordial cosmos, potentially revealing a hidden layer of reality that has been subtly influencing the composition of everything we see since the very beginning of time. Just when we think we've begun to understand the rules of the cosmos, the universe sends us messengers that break them entirely. Imagine a single subatomic particle, a proton or an atomic nucleus, hurtling through the void with so much energy that its kinetic energy is comparable to that of a professionally thrown baseball. This is not science fiction. These are ultra-high energy cosmic rays, the most energetic particles known to exist, and their very presence at such mind-numbing energies presents us with a paradox that cuts to the core of modern physics. The puzzle is known as the GZK cutoff paradox, and it forces us to question our understanding of the very fabric of space-time on its grandest scales. To grasp the paradox, we first need to understand the theoretical barrier that these particles seem to be breaking. The GZK cutoff, named for physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin, who predicted it in 1966, is a fundamental energy limit imposed by the universe itself. The logic goes like this: space is not completely empty. It is filled with the faint, cold afterglow of the Big Bang, the cosmic microwave background radiation. This sea of photons is the oldest light in existence, and it permeates every cubic centimeter of the cosmos. Now, when an ultra-high energy cosmic ray, traveling at nearly the speed of light, encounters one of these low-energy SIMB photons, a catastrophic interaction should occur. According to Einstein's special relativity, from the perspective of the superfast proton, that once gentle SIMB photon is massively blue-shifted, appearing as a powerful high-energy gamma ray. When these two collide, they can create new particles, most notably a pion. This process saps a tremendous amount of energy from the cosmic ray. Over intergalactic distances, this process should act like a cosmic speed limit, putting a hard cap on how far such energetic particles can travel. Any cosmic ray with an energy above about 6 times 10 to the 19th electron volts, a number known as the GZK cutoff, should be effectively slowed down within a distance of about 150 million light years. It should be impossible for us to detect particles from more distant sources at energies beyond this limit. This is where the observations get deeply strange. Massive state-of-the-art facilities like the Pierre Auger Observatory in Argentina and the telescope array in Utah are designed to detect these rare, ultra-high energy events. They don't catch the particles directly as they are destroyed in the atmosphere. Instead, they observe the enormous cascades of secondary particles, air showers, that result when a cosmic ray slams into the air molecules at the top of our atmosphere. The data from these painstaking observations has revealed something startling. We are detecting cosmic rays with energies significantly above the GZK cutoff. These particles are arriving at Earth with energies that, according to our best theories, they should have lost long before they reached us. It's as if marathon runners were arriving at the finish line, not only without breaking a sweat, but with more energy than they had at the starting gun. The universe, it seems, is cheating. So how are these particles beating the cosmic speed limit? Scientists have proposed several compelling and some truly radical explanations. The most straightforward idea is that these ultra-high-energy cosmic rays aren't coming from the distant universe at all, but from relatively nearby sources within the so-called galactic horizon of 150 million light-years. In this scenario, the particles don't have enough time to be significantly slowed down before they reach us. The hunt is on for these local cosmic accelerators. What celestial object could possibly impart such staggering energy to a single particle? Prime candidates include active galactic nuclei, where matter is violently heated as it spirals into a supermassive black hole, or perhaps gamma-ray bursts, the most energetic explosions in the universe since the Big Bang. The problem is, when we trace back the arrival directions of these ultra-high-energy events, they don't consistently point back to any obvious, powerful sources within our local cosmic neighborhood. The sources, if they are local, remain shrouded in mystery. This lack of clear local sources has given weight to a far more mind-bending possibility that our understanding of physics itself is wrong. One of the most profound potential solutions is a violation of Lorentz invariance. This is a cornerstone principle of Einstein's special relativity, which states that the laws of physics are the same for all observers, regardless of their relative velocity. Lorentz invariance is what gives us the equations for time dilation and length contraction, and it underpins our entire modern framework of particle physics. If Lorentz invariance is violated, even at an almost imperceptible level at these extreme energies, the rules of the game could change. The interaction cross-section between the cosmic ray and the SIMB photon could be altered, making the energy-sapping pion production less likely. In such a universe, the GZK cutoff would effectively be lifted or shifted to a much higher energy, allowing these particles to travel across the cosmos unimpeded. This isn't just a minor tweak, it would represent a fundamental breakdown of relativity at the highest energies and could be a hint of a deeper theory of quantum gravity, a regime where space-time itself may have a discrete, grainy structure. We're left with a classic scientific standoff. On one hand, we have a conservative explanation that relies on unknown but relatively conventional astrophysical sources lurking in our intergalactic backyard. On the other, we have a revolutionary idea that would require us to rewrite the textbooks of fundamental physics. The GZK cutoff paradox is more than just a curious anomaly. It is a direct experimental probe into the most extreme regimes of energy and distance. Each ultra-high-energy cosmic ray that strikes our atmosphere is a messenger from the most violent processes in the universe, and its very existence at such energies is a bold challenge to our current models. By continuing to collect these rare events and map their origins, we are not just studying cosmic rays, we are stress-testing the very laws of nature, searching for the subtle cracks that might finally lead us to a deeper, more complete theory of everything. Yet even as we grapple with particles that defy cosmic speed limits, an equally startling challenge to established science has emerged not from the vastness of space, but from within the heart of the atom itself. In the world of nuclear physics, the rules are famously strict. The powerful force that binds protons and neutrons together in an atomic nucleus is a delicate balancing act, and one of its most fundamental principles is the stability offered by pairing. Protons and neutrons prefer to exist in twos, creating stable, tightly bound systems. A lone neutron, isolated from a nucleus, is unstable and will decay into a proton in a matter of minutes. A system of two neutrons alone, a dinitron, is not bound and simply falls apart. So the idea of a stable cluster of four neutrons, with no protons at all to provide balancing positive charge, was long considered an absolute impossibility. It was a nuclear ghost, a configuration that the strong nuclear force simply should not allow. This is what makes the reported observations of the tetraneutron so profoundly disruptive. The story begins in 2001 with a team of researchers in France firing beams of unstable lithium isotopes into a small lithium target. Their goal was to study other nuclear reactions, but in the resulting debris, they detected signals that were incredibly difficult to explain. The data suggested the fleeting existence of a resonant state, a particle that lived for just a fraction of a nanosecond composed of four neutrons. The statistics were marginal, and the physics community reacted with deep skepticism. How could such a thing hold together for any amount of time? The strong force between two neutrons is simply not attractive enough to overcome the tremendous repulsive forces at play. Without protons to act as a kind of nuclear glue, the whole system should blow itself apart instantly. Many scientists dismiss the finding as a statistical fluke or an experimental misreading, an artifact of the complex detection methods, but the ghost wouldn't die. Over a decade later, a much more robust experiment at the RIKN Research Institute in Japan sought to settle the debate. They used a different, more precise approach, colliding a beam of helium-8, a highly unstable isotope, with a stable helium-4 target. The collision was meticulously designed to strip away 4 protons in a single clean event, potentially leaving behind a cluster of 4 neutrons. The results, published in 2016, were startlingly clear. They observed a distinct resonance with a lifetime of about 10 to the power of negative 22 seconds, an almost unimaginably brief flicker of existence, but long enough in the nuclear world to be significant. This was not a stable particle, but a temporary, resonant state that defied the conventional nuclear models. The evidence was now too strong to simply ignore. If the tetraneutron is confirmed to be a true, albeit short-lived, resonant state, the implications would force a major rewrite of our understanding of the strong nuclear force. Our current models, which have been spectacularly successful at explaining the properties of thousands of known atomic nuclei, simply do not have a natural place for a bound system of 4 neutrons. This means there must be a facet of the nuclear force that we have not yet accounted for, a subtle interaction between multiple neutrons that only becomes significant when they are assembled in this specific, pure neutron configuration. It would be like discovering that a fundamental ingredient in a recipe you've used for years has a hidden property that only appears when you use it in a way you never thought to try. Theorists have scrambled to adjust their equations, exploring exotic possibilities like a new, very strong attractive force that emerges between neutrons when they are in a specific quantum state, or that the 4 neutrons arrange themselves in a unique, perhaps even a slightly enlarged, neutron molecule that is temporarily bound. The ongoing debate within the physics community is a fascinating display of scientific caution meeting tantalizing discovery. Skeptics continue to question whether the signals are truly from a tetraneutron resonance, or if they could be explained by a more complex, but ultimately conventional, interaction involving the simultaneous production of multiple unbound particles that merely appear to be a single entity. Confirming the existence of the tetraneutron requires not just one, but multiple independent experiments using different techniques to all arrive at the same conclusion. The hunt is now on at particle accelerator laboratories around the world to reproduce the RIKN results and measure the properties of this elusive object with even greater precision. What is ultimately at stake here is more than just a new entry in the particle zoo. The tetraneutron represents a potential new form of matter. If such pure neutron clusters can exist, even momentarily, it opens up the possibility that they could play a role in the most extreme environments in the universe, such as in the crushing densities found inside neutron stars. The outer crust of a neutron star is a bizarre landscape where atomic nuclei are packed together in a sea of free neutrons. Could tiny, transient neutron clusters like the tetraneutron form in this soup and influence the star's properties? The very possibility forces us to reconsider what is feasible in the nuclear realm, reminding us that even the most established laws can harbor secrets, waiting for the right experiment to reveal a deeper, more complex layer of reality. If the tetraneutron challenges our understanding of the forces within the atom, then our next anomaly threatens to overturn one of the most sacred principles in all of physics, a law that has been the bedrock of rocketry and spaceflight since its inception. This is the bizarre and controversial story of the electromagnetic drive, or M drive, a device that promised the impossible, thrust without propellant. For decades, the idea was relegated to the fringes of science, a fantasy akin to pulling oneself up by one's bootstraps. But then, a handful of experiments began to report a tiny, persistent, and utterly inexplicable signal that refused to go away. The core principle the M drive seemingly violates is the conservation of momentum, a fundamental law which states that for every action, there is an equal and opposite reaction. This is why rockets work. They burn fuel and expel mass out the back, and the reaction to that expulsion pushes the rocket forward. The M drive, in its most basic proposed form, has no fuel to expel. It's a sealed asymmetrical metal cavity, shaped roughly like a truncated cone or a bucket. The idea is that you pump microwave energy into this cavity where the photons bounce around, resonating. According to its proponents, the tapered shape of the chamber causes radiation pressure, the tiny push exerted by light, to be greater on the larger end wall than the smaller one, creating a net thrust in one direction. To most physicists, this sounds like trying to move a car by sitting inside and pushing on the windshield. Without throwing something out the back, the entire system's center of mass shouldn't budge. Yet the experimental claims were what ignited the firestorm. The story gained real traction in the early 2000s when a British inventor named Roger Scheuer published his results. Skepticism was extreme, but then other teams, including a group in China and later a team led by NASA EagleWorks Laboratory under Harold "Sonny" White, began building their own versions. Their meticulous experiments conducted in vacuum chambers to eliminate the effects of air reported the same baffling result. When they powered up the microwave resonator, their ultra-sensitive torsional pendulums, devices designed to measure infinitesimally small forces, detected a tiny but consistent thrust. We're talking about forces on the order of micronewtons, a push so slight it's comparable to the weight of a single eyelash. But in the world of precision physics, that's a signal, and it was a signal that appeared to point in one direction, seemingly generated from nothing. Faced with this potential violation of a cornerstone law of physics, scientists scrambled for explanations that wouldn't require burning the textbooks. One of the most discussed theoretical attempts involved the quantum vacuum. This isn't empty space, but a seething, frothing sea of virtual particles that constantly pop in and out of existence, borrowing energy from the vacuum for a fleeting moment before annihilating each other. The idea was that the M drive was somehow interacting with this quantum foam. Perhaps the microwaves in the cavity were pushing against these virtual particles, effectively using the quantum vacuum as a reaction mass, a propellant that exists everywhere. This would mean the drive wasn't truly reactionless, it was just pushing against something we hadn't considered. However, most particle physicists found this idea deeply problematic. Virtual particles, by their very definition, aren't real particles you can push against in any classical sense. They are mathematical artifacts of quantum field theory. Trying to use them for thrust is widely seen as misunderstanding their fundamental nature. Another avenue of investigation looked at possible experimental errors and unconventional physics. Could the measured thrust be an artifact of the experimental setup itself? The most persistent skeptic and a key figure in this story is German physicist Martin Tajmer. His team at the Dresden University of Technology built an incredibly precise version of the experiment, using a sophisticated pendulum in a vacuum and employing multiple methods to cancel out any external influences, including the Earth's magnetic field. Initially, Tajmer's group also measured a thrust, but then they went a step further. They realized that the simple act of running electrical power to the device through wires was causing a subtle thermal effect. As the device heated up, these wires expanded ever so slightly, which was enough to impart a tiny force on their measuring apparatus. When they accounted for this thermal expansion effect, the anomalous thrust signal in their experiment disappeared. This finding pointed toward a much more mundane explanation. The thrust was not a new physics phenomenon, but a sophisticated form of measurement error, a classic case of not accounting for all the variables in an exquisitely sensitive system. Despite these damning results from Tajmer and others, the embers of the M-drive controversy have not been fully extinguished. Proponents argue that not all the positive results can be explained by thermal effects, and that the sheer persistence of the signal across different laboratories and different designs is highly suggestive. The debate raged on internet forums and in scientific conferences for years, a perfect example of how extraordinary claims demand not just extraordinary evidence, but also the relentless elimination of every possible conventional explanation. For a brief, thrilling moment, the M-drive offered a vision of a future with fantastical propulsion systems that could take us to the stars without the need to carry colossal amounts of fuel. Today, the scientific consensus has largely settled on the side of skepticism, viewing the M-drive as a fascinating lesson in experimental rigor and a cautionary tale about the seductive power of a revolutionary idea. It remains a powerful anomaly, not necessarily for the physics it might have unveiled, but for the intense global scientific scrutiny it provoked, demonstrating just how hard it is to truly kill an idea that promises to rewrite the rules of the game. While our cosmic inventory of dark matter remains deeply mysterious, a different kind of missing matter problem has been haunting astronomers for decades, one involving the very ordinary, tangible stuff we're made of. This is the case of the missing baryons. The term baryon might sound technical, but it simply refers to the family of particles that make up the atoms of our everyday world, the protons and neutrons in the nuclei of every star, planet, and human body. Based on the incredibly precise measurements of the cosmic microwave background, we have a very firm handle on how much of this ordinary matter should have been created in the Big Bang. The Planck satellite data gives us a precise cosmic recipe. Baryonic matter should account for about 4.8% of the total mass energy content of the universe. It's a number we trust implicitly, yet when astronomers go out and take a census of all the visible matter in the modern universe, adding up all the light from stars, the glowing gas within galaxies, the vast clouds of cold hydrogen, and the hot plasma in galaxy clusters, they come up dramatically short. The total they find is only about 60 to 70% of what the CMB says should be there, whereas the other 30 to 40% of the universe's ordinary matter. It's a staggering amount to be missing. We are not talking about some exotic unknown substance here. We are talking about the same protons and neutrons that constitute everything we can see and touch. It's as if you meticulously calculated the total amount of wood needed to build a house, purchased every last plank, and then when construction was finished, found that a third of your lumber was simply gone without a trace. This discrepancy sent scientists on a cosmic scavenger hunt, and the prime suspect for this hidden reservoir has a name as evocative as the mystery itself, the warm-hot intergalactic medium, or WIM. Theorists realized that the missing baryons were unlikely to be hiding in plain sight. They probably weren't clumped together into faint, distant stars or cold, dark galaxies we hadn't spotted. Instead, the leading idea is that this matter is distributed in a vast, tenuous web of incredibly hot, ionized gas that fills the spaces between galaxies and galaxy clusters. This is the cosmic web, the large-scale structure of the universe, and the WIM is the gossamer thin gas that traces its filaments. The problem is, this gas is fiendishly difficult to detect. It's far too hot to emit visible light, and it's so diffuse that it doesn't absorb much light either. It's a ghostly presence, a cosmic fog that permeates everything, but reveals itself only under very specific conditions. The hunt for the WIM has been a triumph of indirect detection and clever astronomical techniques. Since we can't see this gas directly, we have to catch it in the act of doing something else. The most successful method has been to use bright, distant objects as cosmic flashlights. When the light from a brilliant quasar travels across billions of light years to reach us, it passes through these invisible filaments of the WIM. The highly ionized oxygen atoms in this superheated gas can absorb specific, very high energy wavelengths of this background light, notably in the far ultraviolet and soft X-ray parts of the spectrum. It leaves a distinct, though incredibly faint, fingerprint in the quasar spectrum. Finding these absorption lines is like finding the silhouette of a ghost against a bright light. You can't see the ghost itself, but you can see where it blocks the light. For years, these signatures were just a theoretical prediction, but then painstaking observations with space telescopes like XMM, Newton, and Chandra began to find them. Astronomers would point these powerful instruments at a quasar, and after collecting light for dozens or even hundreds of hours, would finally see the telltale dips in the X-ray spectrum that could only be caused by the warm-hot intergalactic medium. More recently, a different and equally ingenious technique has provided even stronger evidence. It involves using the cosmic microwave background itself as the backlight. The Sunyaev-Zeldovich effect occurs when the CMB's photons, on their long journey to Earth, pass through a massive cloud of hot electrons, like those found in the WIM. When these low-energy CMB photons collide with the high-energy electrons in the gas, they get a slight energy boost, a process known as inverse Compton scattering. This creates a very specific, subtle distortion in the CMB's temperature in the direction of that gas cloud. By mapping these distortions across the sky, astronomers can effectively trace the distribution of this hot, diffuse plasma. Using data from the Planck satellite, researchers have been able to perform a statistical stacking analysis. combining the signals from vast numbers of galaxy pairs to build up a detectable SZ signal from the WIM filaments connecting them. This is like listening for a single quiet voice in a roaring stadium. By combining the audio from thousands of microphones pointed in the same general direction, the random noise cancels out and the faint signal emerges. The evidence from these methods is now converging to suggest that the WIM does indeed contain the vast majority of the universe's missing baryons. It seems the mystery is close to being solved, not with the dramatic discovery of a new object, but with the slow, meticulous piecing together of a faint signal from a medium that was there all along. The resolution of the missing baryon problem is a profound reminder of the nature of our universe. Most of the ordinary matter is not locked up in brilliant galaxies or shining stars. Instead, it exists in a form that is almost perfectly invisible to us, a sparse, superheated ocean of gas that constitutes the true backbone of the cosmic web, the hidden scaffolding upon which the visible universe is built. While we often picture planetary weather as a chaotic swirl of storms and clouds, one world in our solar system presents an atmospheric feature of such perfect geometric precision that it seems almost artificial. At Saturn's North Pole, a colossal six-sided jet stream has been raging for decades, a stunning hexagon larger than our entire planet that stands as one of the most striking and enduring mysteries in our cosmic neighborhood. This is not a feature painted on the surface, but a persistent wave pattern in the atmosphere itself, a howling river of wind where each of the six sides is longer than the diameter of Earth. For over 40 years since it was first glimpsed by the Voyager probes in the early 1980s and then studied in exquisite detail by the Cassini spacecraft, this hexagon has maintained its shape, a stable, rotating puzzle etched into the clouds of a gas giant. What makes the Saturn hexagon so baffling to physicists is its defiance of typical fluid dynamics. In nature and especially in planetary atmospheres, we expect turbulence and rotation to create circular patterns like the spiraling arms of a hurricane or the vast oval of Jupiter's great red spot. Fluids and gases naturally tend toward rounded, amorphous shapes because they are governed by forces that dissipate energy and smooth out sharp angles. A stable geometric form with six straight sides is completely counterintuitive. It's like expecting a swirling eddy in a river to suddenly form a perfect square. The hexagon isn't just a superficial cloud pattern either. It's a deep-rooted atmospheric structure, a jet stream where winds scream at speeds of over 320 kilometers per hour, racing around the geometric path. The entire structure rotates with a period of about 10 hours and 30 minutes, which intriguingly appears to be close to the rate at which the planet itself emits radio waves, a potential clue to its interaction with Saturn's deep interior. To unravel this mystery, scientists have turned to laboratories here on Earth, attempting to recreate the conditions that could spawn such an anomaly. In one famous set of experiments, researchers placed a cylindrical tank of fluid on a rotating table, representing a spinning planet. At the center of this tank, they placed a smaller rotating ring which created a shear zone, a region where the fluid was moving at different speeds, mimicking the steep velocity gradients in Saturn's atmosphere. When they spun the system at just the right speed, something remarkable happened. Instabilities in the fluid didn't produce a chaotic mess. Instead, they coalesced into stable, polygonal shapes. They could create squares, pentagons, and most frequently, hexagons. This demonstrated that under specific conditions of rotation and shear, the atmosphere can naturally organize itself into standing wave patterns that manifest as geometric shapes. The hexagon in this view is a kind of giant planetary scale standing wave, frozen in place by Saturn's rapid rotation and the specific profile of its polar winds. However, while laboratory models can create the shape, they often struggle to replicate its astounding longevity. The experimental polygons are often fleeting, lasting for a few rotations before degrading. Saturn's hexagon, by contrast, has been observed for decades, weathering seasonal changes as the planet's North Pole experienced years of darkness and then sunlight. This incredible persistence suggests there are factors at play beyond a simple sheer instability. Some theories propose that the hexagon is rooted much deeper in the planet than we initially thought, perhaps interacting with powerful jet streams that dive thousands of kilometers below the visible cloud tops. The planet's own internal heat and complex, layered atmospheric structure may be providing the continuous energy needed to maintain this precise pattern against the dissipating forces of turbulence. It's a delicate balance, a planetary feedback loop that has kept this six-sided figure spinning like a cosmic top for generations, a permanent work of celestial art whose creator is the invisible hand of physics itself. From the geometric perfection of Saturn's hexagon, we now leap across the cosmos to a phenomenon defined by its breathtaking brevity and staggering power, the fast radio burst. Imagine a flash of radio light so brilliant that for a few thousandths of a second it outshines entire galaxies. These are not gentle signals, they are cosmic screams, blasting across millions or even billions of light years to deliver their immense energy in a blink so fast that if you blinked your own eyes, you would miss it thousands of times over. The story of FRBs begins not with a grand plan, but with a moment of serendipitous discovery buried in old data. It was 2007 when West Virginia University astronomer Duncan Lorimer and his student David Narkevic were sifting through archival observations from the Parkes Radio Telescope in Australia. These recordings were from 6 years prior, meant to study pulsars, the spinning corpses of dead stars. As they scanned the data, they found something that shouldn't have been there, a single colossal spike of radio energy that leaped out of the background noise, a burst lasting just 5 milliseconds. It was so powerful and so brief that for a long time, many in the astronomy community were deeply skeptical, suspecting it was some form of terrestrial interference, a glitch from a microwave oven on the observatory grounds, or an errant satellite signal. But this was the Lorimer burst, the first of its kind, and it opened a door to a hidden dimension of the universe. For years, these events were so rare and fleeting that they remained cosmic phantoms. The true revolution began when new, more powerful telescopes and sophisticated software allowed astronomers to catch them in real time. The breakthrough that shattered all previous understanding came in 2016 with the detection of a source known as FRB 121102. This wasn't a one-off event. Astonishingly, it repeated. This single observation immediately ruled out the leading theory that fast radio bursts were caused by cataclysmic, one-time, only events like two neutron stars colliding in a final destructive embrace or a massive star collapsing into a black hole. You cannot have a repeat performance from an explosion that destroys the source. The repeating FRBs fundamentally changed the game, pointing toward a source that could survive its own outburst, something that could fire again and again, like a cosmic engine with a stuck ignition. This discovery bifurcated the FRB family into two distinct classes, the apparent one-off bursts, which may still be caused by cataclysms, and the prolific repeaters, which require a completely different and perhaps even more exotic physical explanation. So what cosmic engine can produce such violent, fleeting, and sometimes repeating flashes? The hunt for a progenitor has become one of the most thrilling detective stories in modern astrophysics, with suspects ranging from the well-established to the wildly speculative. The current leading candidate is the magnetar, a type of neutron star that takes the already extreme physics of a stellar corpse and cranks it to 11. A magnetar possesses a magnetic field so intense it is 1,000 trillion times stronger than Earth's. It's a magnetic field so powerful that it could strip the information from every credit card on the planet from halfway across the solar system. The theory is that these stars can experience starquakes, sudden fractures in their incredibly dense crystalline crust. When the crust snaps, it releases a titanic amount of energy, shaking the star's immense magnetic field and converting that seismic energy into a blistering flash of radio waves that we see as an FRB. Supporting this idea, in April 2020, a magnetar within our own Milky Way galaxy, named SGR 1935 plus 215, erupted in a burst of radio energy that, while much weaker than the extragalactic FRBs, shared a striking resemblance in its profile. It was a smoking gun, demonstrating that at least some magnetars are indeed capable of producing these spectacular radio bursts, but the magnetar model, while compelling, doesn't answer every question. Some repeating FRBs show behaviors that are almost playful, with periods of intense activity followed by months of radio silence, and some even emit bursts at lower frequencies than others, suggesting multiple mechanisms might be at work. This has led to other fascinating theories. One involves an extreme version of a pulsar, where a highly magnetized neutron star is orbiting through a dense cloud of debris left over from the supernova that formed it. As the star plows through this material, the resulting shockwaves could generate the intense radio flashes. Another, more complex idea posits the interaction between a neutron star and its companion in a binary system, where material transferring between the stars creates violent, episodic eruptions. And then, of course, there is the most sensational hypothesis that captures the public imagination: the possibility of advanced alien civilizations. Could these bursts be the leakage from unimaginably powerful transmitters, propelling interstellar ships with light sails, or perhaps even deliberate beacons? While scientists rightly consider this the least likely explanation, the universe has a prolific history of creating natural phenomena far more exotic than we can imagine. The very fact that the energy requirements for some FRBs are within the conceivable, if colossal, scale for a Type 2 civilization on the Kardashev scale means it cannot be completely dismissed out of hand. It remains a thrilling, if remote, possibility in the background of the investigation. The key to unlocking the FRB mystery lies not just in detecting more of them, but in pinpointing their exact cosmic addresses. This is where a new generation of telescopes has completely transformed the field. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, is a revolutionary instrument. Unlike a traditional steerable dish, CHIME is a static array of cylindrical antennas that stares fixedly at the sky as the Earth rotates, scanning a huge swath of the heavens every single day. Since it came online, CHIME has gone from detecting a handful of FRBs to discovering hundreds, even thousands, turning them from rare curiosities into a common cosmic population. This statistical power is crucial for understanding their true nature. Even more important has been the role of rapid response networks and telescopes that can see in multiple wavelengths. When a powerful FRB is detected by a radio telescope like CHIME or ASCAP in Australia, automated alerts are sent out to observatories around the world and in space within seconds. This allows the Hubble Space Telescope, the Chandra X-ray Observatory, and large optical telescopes on the ground to swing into action, searching for a counterpart, a faint, glowing afterimage, or an X-ray flash that could identify the host galaxy and the local environment of the burst. This multi-messenger approach has been spectacularly successful, localizing numerous FRBs to their host galaxies, which range from massive, stately spirals to tiny, chaotic dwarf galaxies where star formation is rampant. This diversity itself is a clue, suggesting that the conditions for creating FRBs are not exclusive to one particular type of galactic neighborhood. Perhaps the most profound revelation from these precise localizations is the role of FRBs as cosmic probes. Each burst, as it travels across the vast, empty intergalactic medium, carries a hidden imprint of its journey. The different radio frequencies that make up the burst travel at very slightly different speeds, with lower frequencies arriving a fraction of a second after the higher ones. This dispersion measure tells astronomers the total number of free electrons the signal has passed through, a direct gauge of the amount of ionized gas or baryonic matter between us and the source. In a stunning convergence of mysteries, FRBs are now being used to independently weigh the universe's missing baryons, the very same ordinary matter we hunted for in the warm, hot intergalactic medium. By analyzing the dispersion of bursts from galaxies at different distances, astronomers can effectively measure the density of the cosmic web's filaments, confirming that the WIM is indeed the final resting place for the universe's lost atoms. This transforms FRBs from mere cosmic oddities into indispensable tools for mapping the large-scale structure of the cosmos, using their fleeting flashes to illuminate the dark, invisible threads that connect all of creation. But as we venture from the cosmic scale of fast radio bursts to the intimately familiar world of childhood memories, we encounter an anomaly of a completely different kind, one that doesn't reside in deep space, but within the very fabric of our collective consciousness. This is the bizarre case of the Berenstain Bears, or rather, as all physical evidence insists, the Berenstain Bears. For countless people across the globe, the memory is vivid and unshakable. The beloved children's book family they grew up with was named Berenstain, pronounced Berenstein. They can picture the book covers, recall the animated television shows, and would swear on a stack of those very books that the name ended with an E. Yet when they encounter the books today, perhaps while reading to their own children, they are met with a jarring reality. The name is, and apparently always has been, Berenstain, spelled with an A. This collective specific false memory has become the poster child for a phenomenon known as the Mandela effect, named for the widespread recollection of Nelson Mandela dying in prison in the 1980s, despite his actual death in 2013. The psychological explanations for this are robust and fascinating, centered on the concept of memory reconstruction. Our brains are not perfect video recorders, they are associative organs that constantly take shortcuts. When we encounter the name Berenstain, our minds likely autocorrect it to a more familiar and phonetically predictable pattern. The Stein ending is extremely common in English surnames, think Frankenstein, Einstein, or Goldstein. The Stein ending, by contrast, is less common and can carry slightly negative connotations, so our brain, seeking efficiency and familiarity, substitutes the unusual with the common, creating a Berenstain memory that feels entirely real. This is reinforced by social corroboration. When we hear others pronounce it Berenstain, it solidifies the false memory in a self-reinforcing loop. The memory isn't a deliberate lie, it's a confident and detailed mental reconstruction that our brain presents to us as fact. However, for those who experience this effect, the purely psychological explanation can feel insufficient. The memory is often so specific and so widely shared that it sparks more speculative and far more thrilling theories. Could this be a glimpse of parallel universe leakage? The idea posits that in another very similar reality, the books truly were spelled Berenstain. According to this hypothesis, our consciousness has somehow brushed against or briefly merged with that other timeline, leaving us with residual memories that conflict with our current reality. We aren't misremembering, we are remembering correctly, but from a different version of our past. This taps into a deep-seated human curiosity about the nature of reality and the possibility of a multiverse, transforming a simple spelling error into a potential crack in the universe. What makes the Berenstain Bears example so uniquely powerful is its anchoring in a universal experience of childhood. These books are foundational artifacts for many people, read repeatedly during a period of life when memories are being intensely formed. The dissonance isn't about a minor historical detail, it feels like an alteration of one's personal history, a small but profound glitch in the matrix of one's own life story. This personal stake, combined with the sheer number of people who share the identical, specific memory, elevates it beyond a simple mistake into a genuine cultural phenomenon. It forces us to confront the unsettling truth that our past is not a fixed, objective record, but a story our mind tells us, a story that can be edited without our knowledge, leaving us to wonder what else we might remember that never actually was. From the curious quirks of human memory, we now return our gaze to the cold, hard data of the cosmos, to a glaring anomaly radiating from the very heart of our own Milky Way. Imagine pointing the most powerful gamma-ray telescope ever built toward the center of our galaxy, expecting to see the diffused glow of known cosmic processes, and instead finding a mysterious excess brilliance that forms a perfect sphere of light around the galactic core. This is the galactic center excess, a discovery that has ignited one of the most intense and ongoing debates in modern astrophysics, pitting the tantalizing possibility of dark matter detection against the stubborn complexity of more conventional celestial objects. The story begins with the Fermi Gamma Ray Space Telescope, a monumental observatory launched by NASA in 2008. Its mission is to map the high-energy universe, to see the sky not in the gentle light of stars, but in the violent, penetrating glare of gamma rays, the most energetic form of light produced by the universe's most extreme phenomena. When scientists pointed Fermi at the galactic center, a region teeming with activity, they meticulously subtracted all the known sources of gamma rays. They accounted for the diffuse background from cosmic rays colliding with interstellar gas, the brilliant point sources of pulsars, and the powerful jets from the supermassive black hole, Sagittarius A star. But once all these expected signals were removed, a significant and unexplained residue remained. This wasn't a few scattered points of light, it was a smooth, spherical haze of gamma-ray emission extending thousands of light years from the core, an energetic glow that our standard models of galactic physics simply could not account for. The moment this excess was identified, a thrilling hypothesis immediately took center stage: dark matter annihilation. The theoretical framework for this is both elegant and compelling. We know that dark matter, whatever it is most densely concentrated in the centers of galaxies, including our own. If dark matter is made of weakly interacting massive particles, or WIMP, then these particles are their own antimatter counterparts. This means that when two WIMP collide, they could annihilate each other, converting their entire mass into pure energy in accordance with Einstein's famous equation, E equals mc squared. The resulting energy would manifest as a shower of standard model particles, including gamma rays. The predicted energy signature of the gamma rays from the galactic center aligns remarkably well with what would be expected from the annihilation of a WIMP with a mass between 30 and 40 gigaelectronvolts, a mass range that is a prime target for many underground dark matter detection experiments. For a brief electrifying period, it seemed that Fermi might have provided the first indirect observational evidence for the elusive particles that make up the vast majority of matter in the universe. However, extraordinary claims require the relentless elimination of all ordinary explanations, and the galactic center is anything but an ordinary place. Astronomers advocating for a more conservative astrophysical explanation pointed their fingers at a different hidden population of objects, millisecond pulsars. A pulsar is a rapidly spinning neutron star, the ultra-dense core left behind after a supernova explosion, which emits beams of radiation like a cosmic lighthouse. A millisecond pulsar is an even more extreme version, spun up to incredible rotational speeds by accreting matter from a companion star. These objects are known to emit powerful gamma rays. The central argument here is that the Fermi telescope, while powerful, may not have the resolution to distinguish a truly smooth, diffuse glow from the combined light of thousands of faint, point-like millisecond pulsars that are too dim to be seen individually. In this view, the galactic center excess isn't a sign of new physics. It's simply the collective hum of a vast, previously unresolved orchestra of dead stars, their combined gamma ray emissions creating the illusion of a smooth, spherical haze. The debate has therefore settled into a sophisticated game of cosmic forensics, with each side marshalling evidence from increasingly detailed analyses. Proponents of the dark matter interpretation point to the excess's remarkable morphological smoothness and its perfect spherical symmetry. This geometry fits beautifully with the predicted distribution of dark matter, which should form a smooth, round halo. They argue that while pulsars could explain the energy spectrum, it is much harder for them to naturally create such a perfectly spherical distribution, as stars and stellar remnants tend to be distributed in a more flattened, disk-like structure. On the other side, teams have used advanced statistical methods to search for the telltale sign of a pulsar population, statistical fluctuations. In regions where the excess glow is brightest, some analyses have claimed to find a granularity in the gamma ray map, subtle clumpiness that is more consistent with a collection of discrete point sources than with a perfectly smooth dark matter signal. It's akin to looking at a distant city at night. From a great distance, its light may appear as a uniform glow, but with a powerful enough telescope, you can start to resolve the light into individual street lamps and windows. This scientific tug-of-war is far from over, and it perfectly illustrates the challenges of doing cutting-edge science in the most crowded and complex region of our galaxy. The galactic center is a place of immense stellar density, powerful magnetic fields, and turbulent gas, all of which can create or obscure the very signals we're trying to interpret. New observations continue to pour in, and with them, new interpretations. Some recent studies have attempted to bridge the divide, suggesting that the truth may be a mixture of both phenomena, that a significant portion of the excess could indeed be from millisecond pulsars, but that a component of it might still be the long-sought signature of dark matter annihilation. The resolution of this mystery likely awaits the next generation of gamma-ray telescopes with even greater resolution and sensitivity, capable of definitively resolving or ruling out a point source population. Until then, the galactic center excess remains one of the most compelling and frustrating anomalies in the sky, a radiant enigma at the heart of the Milky Way that continues to whisper promises of a dark universe, while forcing us to first grapple with all the brilliant, complicated astrophysics of the one we can see. While the search for the missing baryons reveals the hidden, tenuous structures within our own cosmic epoch, some of the most profound anomalies are painted on the very first canvas of existence, the cosmic microwave background. We've already encountered the unsettling large-scale alignment of the axis of evil, But there is another, equally bizarre feature on this ancient map that has captivated and perplexed cosmologists: a spot. Not just any spot, but a colossal, puzzlingly cold one. This is the CMB cold spot, a region in the constellation Eridanus so significantly colder than its surroundings that its sheer size and statistical unlikelihood have forced scientists to consider explanations ranging from the merely strange to the truly universe-shattering. The cold spot was first identified in data from NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, in 2004, and its existence was later confirmed with even greater precision by the Planck satellite. To appreciate why this feature is so anomalous, you have to understand that the CMB is incredibly uniform, with temperature fluctuations that are mostly tiny, random, and on relatively small scales. These tiny ripples are the seeds of all future structure. The cold spot, however, is a giant. It spans a vast area of the sky over 1.8 billion light years across, and its temperature is about 70 microkelvins colder than the average CMB temperature. Now, 70 millionths of a degree might not sound like much, but in the exquisitely precise world of CMB statistics, this is a massive and highly improbable deviation. The chance of such an extreme, large-scale cold region appearing randomly in the CMB map is less than 2%. It's an outlier so significant that it demands a physical explanation beyond mere cosmic chance. It's a blemish on the face of creation that shouldn't, according to our standard models, be there. When faced with such an anomaly, the first and most logical step is to look for a foreground object that could be casting a shadow, an object within the later universe that lies between us and the CMB and is somehow making that patch of sky appear colder. The most compelling conventional explanation is the supervoid hypothesis. A supervoid is exactly what it sounds like: an enormous, underdense region of space, a cosmic desert spanning hundreds of millions of light years where the density of galaxies is dramatically lower than the cosmic average. If such a void existed along our line of sight to the cold spot, the theory of integrated Sachs-Wolf effect provides a mechanism. As CMB photons pass through a large, matter-deficient region like a supervoid, they must climb out of its gravitational potential well. In an expanding universe dominated by dark energy, the well itself is becoming shallower as the photon travels through it. This means the photon loses less energy climbing out than it gained falling in, resulting in a net loss of energy, which we observe as a cooling, a slight reddening of the CMB light. A sufficiently vast and empty supervoid could, in principle, produce the observed cold spot. The hunt for this hypothetical supervoid became a major astronomical endeavor. Astronomers pointed powerful telescopes at the cold spot region, conducting deep galaxy surveys to map its three-dimensional structure, and they did in fact find a void. A significant underdense region, now known as the Eridanus supervoid, has been identified in that direction. The problem is one of scale. The discovered void, while large, is not nearly large enough or empty enough to account for the profound coldness of the CMB spot through the integrated Sachs-Wolf effect. The energy deficit is simply too great. The void we see can only explain a fraction of the cooling. The majority of the effect remains unaccounted for. It's as if we found a small hill to explain the shadow of a massive mountain. The pieces are there, but the scales just don't match up. This mismatch has led many cosmologists to conclude that the supervoid is likely just a chance alignment, a foreground object that is coincidentally in the right place but is not the true cause of the underlying anomaly. With the primary conventional explanation falling short, physicists have been forced to entertain far more radical ideas. One of the most breathtaking possibilities is that the cold spot is a bruise, a cosmic scar left from a collision with another universe. This idea springs directly from the theory of eternal inflation and the multiverse. In this grand picture, our universe is just one expanding bubble in a vast, frothing meta-universe where new bubble universes are constantly inflating into existence. Occasionally, these bubbles might not form in perfect isolation. They could bump into each other. If another universe in a bubble collided with our own in the distant past, during or just after inflation, the energy released at the boundary of that collision would have left an imprint on the CMB of our universe. The signature of such an event would be a large, circular, and anomalously cold spot, precisely because the collision would have drained energy from that region of space. The cold spot in this view is not a flaw in our universe, but a window to a greater cosmic reality. direct observational evidence that our cosmos is just one island in an infinite archipelago of universes. Of course, such a profound claim is met with justifiable skepticism. The primary counter-argument remains that the cold spot is, after all, just a statistical fluke. Our universe is vast and the SIMB is a complex map. It is not impossible that by pure random chance, a few regions will appear more extreme than our models predict. We might simply be the universe that by luck has a large cold spot, and our human tendency to find patterns and assign profound meaning to randomness is doing the rest. To settle this, scientists continue to analyze the SIMB with ever more sophisticated statistical tools, looking for other, more subtle signatures that could distinguish a multiverse collision from a simple random fluctuation. They also search the sky for other similar anomalies. If the cold spot is unique, it strengthens the fluke argument. If we were to find a second or a third such feature, it would powerfully suggest a recurring physical process like bubble collisions is at work. The SIMB cold spot therefore remains one of the most tantalizing unresolved puzzles in all of cosmology. It sits at the crossroads of the known and the utterly unknown. Is it a mere statistical ghost, a trick of the data that will eventually be smoothed away by better observations? Is it the signature of a supervoid whose properties we still don't fully understand? Or is it, as some daringly suggest, the first empirical evidence for the multiverse, a tangible fingerprint from a reality beyond our own? For now, this frigid patch on the oldest light in the universe holds its secret, a silent, cosmic question mark challenging us to look deeper and wonder if the entirety of existence might be far grander and more interconnected than we ever dreamed. But ancient light can only tell us so much on its own, so to peer even further back into the era when the first stars and galaxies were actually turning on, astronomers turned to a completely different kind of cosmic messenger, distant quasars. These are the impossibly bright cores of active galaxies, powered by supermassive black holes greedily accreting matter. They act as the most powerful flashlights in the universe. As their light travels for billions of years to reach us, it passes through the intergalactic medium. When that medium was still filled with neutral hydrogen, that gas acted like a dense fog, absorbing a very specific portion of the quasars, light in a phenomenon known as the Lyman alpha forest. The signature is unmistakable, a complete Gunn-Peterson trough, a stark, dark band in the quasar spectrum where the neutral hydrogen has absorbed nearly all the light at that wavelength. Finding this trough in the light from the most distant quasars tells us that at that point in cosmic history, the universe was still significantly neutral. The crucial and puzzling observation is that this trough begins to disappear for quasars emitted just after redshift 6, indicating that the fog was lifting, that reionization was largely complete by that time. This, however, is where the tension emerges, creating a serious chronological puzzle. The timeline from the SIMB suggests reionization was a long, drawn-out process, while the evidence from the quasar absorption lines seems to suggest it happened relatively quickly and late. How can we reconcile a process that started very early, as suggested by the SIMB's electron scatter, but also seems to have finished quite abruptly, as seen in the quasar data? This conflict has forced cosmologists to consider much more complex and nuanced models for how the first luminous objects lit up the cosmos. Perhaps reionization wasn't a simple, uniform process like an ocean warming in the sun. Instead, it might have been patchy and inhomogeneous, more like a Swiss cheese being made. In this scenario, the first stars and galaxies ignited in isolated bubbles around them. These bubbles of ionized plasma would have grown and gradually overlapped, eventually filling the entire universe. The SIMB is sensitive to the total number of free electrons created over the entire duration, hence the suggestion of an early start. The quasar absorption lines, however, are like taking a core sample along a single line of sight. If that particular path pierced through a region that was reionized later, it would make the whole process seem to have finished more recently. The plot thickened even further with the launch of the James Webb Space Telescope, which was specifically designed to directly observe the very first galaxies that are thought to have powered reionization. The initial results have been both breathtaking and deeply confounding. JWST has found an astonishing number of surprisingly bright, massive galaxies at extremely high redshifts, far earlier than many models predicted. If galaxies this bright and this numerous existed so soon after the Big Bang, they could have provided more than enough ionizing photons to complete reionization very quickly. This seems to support the quick and late scenario from the quasar data, yet other JWST observations have also shown that many of these early galaxies are surrounded by dense, dusty halos that could have trapped their own ionizing radiation, preventing it from escaping to intergalactic space. This would have made them far less efficient at the process than we assumed, potentially dragging reionization out and supporting the slow and early picture from the SIMB. We are left with a paradox, an abundance of potential power sources for reionization, but a growing uncertainty about how effectively they could actually do the job. Understanding this cosmic dawn is not merely an academic exercise in cosmic chronology. It is absolutely fundamental to the story of how our universe evolved into what we see today. The epoch of reionization was the final major phase transition for the universal medium, setting the initial conditions for all galaxy formation that followed. The way it unfolded dictated the thermal state of the intergalactic gas that would later cool to form new generations of stars. It influenced the growth of the first supermassive black holes and determined the minimum mass for the first dwarf galaxies, as the intense background radiation would have prevented gas from collapsing into small gravitational potential wells. The conflicting timeline we now face is therefore a direct challenge to our most fundamental models of cosmic structure formation. Resolving it will require a delicate triangulation of data, the large-scale statistical picture from the SIMB, the detailed line of sight probes from quasars, and now the revolutionary direct imaging of the galaxy population itself from JWST. Each method provides a different piece of the puzzle, and right now, they don't all neatly fit together. The timeline of reionization remains a blurred and contested chapter in our cosmic history, a reminder that even the most foundational events of creation are still yielding their secrets to our relentless curiosity. Just when we think we've cataloged every possible form a dying star can take, the cosmos unveils a structure of such geometric purity that it defies our expectations of celestial chaos. Drifting through the vast expanse in the constellation Monoceros, a seemingly ordinary star at the end of its life has created something utterly extraordinary, the Red Rectangle Nebula. While its name suggests a simple blocky shape, the reality revealed by the Hubble Space Telescope is far more captivating. This isn't a rectangle at all, but a breathtaking, near-perfect X-shaped structure, a celestial icon of symmetry that appears almost as if it were drafted by a cosmic architect. At its heart lies HG 44179, an aging star that has been steadily shedding its outer layers for thousands of years. What should be a messy, expanding sphere of gas and dust has instead been sculpted into a dazzling pair of hollow, cone-shaped lobes, their edges tracing the straight lines of a perfect X across the sky, with vibrant rungs of red glowing material connecting them like the rungs of a ladder. This precise geometry, emerging from the turbulent death throes of a star, makes the Red Rectangle one of the most visually striking and mechanically puzzling nebulae ever discovered. So how does a star in its final act produce such a flawless geometric form? The formation of this enigmatic X-shape is not the result of a single event, but rather a sophisticated, dynamic dance between the dying star and a hidden companion. The leading theory posits that the central star, HG 44179, is not alone. It is likely part of a closed binary system, orbiting a second star that is deeply shrouded within the thick, dusty disk surrounding them both. It is this disk, a dense, flat torus of gas and dust spun off from the primary star, that acts as the primary sculptor. Imagine a spinning top that begins to wobble or precess as it slows down. Astronomers believe a similar phenomenon is at work here. As the primary star loses mass, it ejects material not in a uniform spherical wind, but in two powerful, narrow jets shooting out from its poles. However, the gravitational tug of the companion star causes the entire system to precess, meaning the rotational axis of the primary star slowly wobbles over time. This wobble makes the direction of these bipolar jets slowly trace out a cone in space. Now picture the dense, dusty disk that surrounds the binary pair. This disk acts like a pair of hourglasses placed tip to tip, constricting the precessing jets and funneling the outflowing material. As the jets precess, they inject material into the surrounding space, but they are only able to escape freely along the thinning poles of the disk. Over centuries, this processing motion, combined with the confining effect of the disk, paints a hollow, cone-shaped structure in the interstellar medium. Because we are viewing this double cone system almost directly from the side, our line of sight cuts through the rims of both cones. The bright, sharp lines we see as the X are not solid walls, but are actually the edges of these hollow cones, where our view passes through the greatest column density of glowing gas. It's an elegant illusion of perspective, where a pair of expanding three-dimensional cones appear to us as a two-dimensional X. The distinctive rungs or ladder features are thought to be periodic pulses of intensified mass loss from the star, creating concentric waves of denser material that are then sculpted by the same outflow. While the processing jet model is the most widely accepted explanation, the astonishing symmetry of the red rectangle has prompted other, more exotic hypotheses. The geometric perfection is so pronounced that some researchers have explored whether magnetic fields play a more dominant role than previously thought. If the central star possesses a strong, well-ordered magnetic field, it could act as a rigid framework, channeling the ionized gas with such precision that it forms these straight, linear edges. This would be similar to how the sun's magnetic field shapes the plasma in solar prominences, but on a vastly larger and more stable scale. Another fascinating possibility involves the specific chemical composition of the nebula itself. The intense red glow which gives the nebula its name comes from a specific type of organic molecule known as polycyclic aromatic hydrocarbons, or PA. These complex carbon-rich compounds fluoresce in ultraviolet light from the central star. The unique distribution and illumination of these pHs might be enhancing the perception of the geometric shape, making the straight lines appear even sharper and more defined than the underlying gas structure might otherwise suggest. The Red Rectangle Nebula, therefore, is more than just a cosmic curiosity. It is a sublime example of how simple physical principles, binary interaction, precession, and perspective can combine to create structures of stunning complexity and beauty. It stands as a powerful testament to the fact that the universe is not always chaotic and messy, but often operates with an underlying mathematical order. This dying star's final masterpiece challenges our preconceptions about stellar death, showing us that even in its demise, a star can create a legacy of perfect symmetry, a temporary monument of gas and dust that will eventually dissipate, seeding the interstellar medium with the complex organic molecules that are the building blocks of future stars, planets, and perhaps one day, life itself. Our journey through cosmic enigmas now brings us from the vast expanse of intergalactic space to the dark, crushing depths of our own world's oceans, where a different kind of mystery is buried under the Arctic ice. Deep beneath the frigid waters, stretching for nearly 1,800 kilometers across the seafloor, lies the Gakkel Ridge, a massive underwater mountain range that is the most isolated mid-ocean ridge on Earth. While this entire region is geologically fascinating, a specific targeted investigation revealed something far stranger than simple volcanic activity. During a scientific expedition to study the ridge's formation, researchers were meticulously mapping the seabed when their instruments picked up a startling signal. In a localized area, they detected a significant and simultaneous anomaly in both the local gravity field and the Earth's magnetic signature. It was a double whammy of geophysical weirdness, a blip in the fundamental forces that seemed to point to something massive, dense, and highly magnetic lurking deep within the rocky crust. This discovery, often referred to in more speculative circles as the Lomonosov Ridge anomaly, immediately captured the imagination of those who look for clues of lost civilizations. The logic is seductive. If an advanced human society existed before a cataclysmic event, perhaps during the last ice age, the Arctic would have been a very different place. Lower sea levels could have exposed parts of these ridges as dry land, habitable plateaus in a more temperate climate. Could this gravitational and magnetic signature be the ghostly imprint of a vast sunken city, its colossal foundations and metallic infrastructure still subtly warping the local physics long after its structures have been crushed and buried by millennia of sediment? The idea of a real-world Atlantis, its existence hinted at not by ancient texts but by the precise measurements of modern science, is a powerful and romantic notion. It suggests we might not need to look to the stars to find evidence of other advanced intelligences. The proof could be lying hidden in the most inaccessible parts of our own planet, waiting for our technology to become sophisticated enough to detect its faint echo. Unsurprisingly, the scientific community approaches this anomaly with a much more grounded, though no less fascinating, set of explanations. The most probable cause lies in the complex geology of mid-ocean ridges themselves. These are places where tectonic plates are pulling apart, allowing hot magma from the Earth's mantle to well up and create new oceanic crust. This process is rarely uniform. Geologists propose that the anomaly could be caused by an extremely dense and highly magnetic body of rock known as an ultramafic intrusion. These are chunks of the Earth's mantle that have been thrust upward without melting, composed of minerals like magnetite and other iron-rich compounds that are both very heavy and powerfully magnetic. A large buried pot of such material would perfectly account for the dual signal, creating a gravitational pull slightly stronger than the surrounding basalt and a corresponding spike in the magnetic field. Another compelling conventional theory involves the formation of a massive sulfide deposit, a huge concentration of metal ores like copper, zinc, and lead that often forms near hydrothermal vents on the seafloor. Over millions of years, volcanic activity could have created a truly enormous deposit, which would also present the exact combination of high density and strong magnetism that was observed. But why would a seemingly terrestrial geological puzzle connect to our broader exploration of space-time mysteries? The link is not in the anomaly itself, but in what it represents, a profound gap in our knowledge. We have more detailed maps of the surface of Mars than we do of our own planet's seafloor. The deep ocean is a legitimate frontier, an alien environment where pressure is immense, light is non-existent, and our ability to explore is severely limited. This lack of direct observation forces us to rely on remote sensing, like gravity and magnetic measurements, to infer what lies below. In this way, the process is eerily similar to how astronomers study the cosmos. We cannot touch a dark matter halo or a distant quasar. We can only observe their gravitational influence and their radiation. The Lomonosov Ridge anomaly is a direct parallel, an unseen, massive object whose properties we must deduce from its subtle effects on the fields we can measure. It is a stark reminder that the scientific method of inferring the unseen from the seen is universal, whether the mystery is buried under 6 kilometers of water and ice or located billions of light years away. This terrestrial enigma humbles us, proving that even on our own world, there are still blank spots on the map that can spawn profound questions, challenging us to discern between the echoes of a lost world and the simple yet incredible wonders of geology. And now we arrive at the final and perhaps most fundamental anomaly on our list, one that challenges our understanding of reality at its very core. It's a phenomenon so bizarre that even its most famous critic, Albert Einstein, could only describe it with a phrase of bewildered frustration: spooky action at a distance. This is the enigma of quantum entanglement, a mysterious connection between particles that defies our classical intuition about space, time, and the nature of information itself. Imagine you have a pair of magical coins, each one sealed in a separate, impenetrable box. You take one box with you on a journey to the farthest star, while the other remains here on Earth. The rule with these coins is that whenever you open a box to look at it, the coin inside will randomly land either heads or tails. There's no way to predict the outcome. Now, according to all our everyday logic, what happens to your coin on that distant star should have absolutely no connection to the coin back home. But with quantum entanglement, here's the spooky part. The moment you open your box and see your coin land on heads, you know with 100% certainty that the other coin, instantly and simultaneously, has landed on tails. This instantaneous correlation, this deep-seated connection that seems to operate faster than the speed of light, is the heart of the quantum mystery that so troubled Einstein. The fundamental challenge that entanglement poses is to two of the most cherished principles in physics: locality and causality. Locality is the common sense idea that objects are only influenced by their immediate surroundings, and that no physical effect can travel faster than light. Causality is the logical flow of cause and effect, where cause must always precede its effect in time. Entanglement appears to shatter both. How can the measurement of one particle here instantly determine the state of its partner, millions of light years away, without some kind of signal passing between them? It seems to suggest a form of communication that operates outside of space and time, a connection so profound that the two particles, once entangled, cease to be independent entities and instead behave as a single unified system, no matter how vast the physical separation between them becomes. Einstein, along with colleagues Boris Podolsky and Nathan Rosen, highlighted this apparent paradox in their famous 1935 EPR paper, arguing that if quantum mechanics predicted such spooky non-local effects, then it must be an incomplete theory. They believed there must be some hidden variables, underlying properties of the particles that were set at the moment of their creation and which predetermined their correlated outcomes, thereby restoring a local causal reality. For decades, the EPR argument remained a philosophical debate, a thought experiment seemingly beyond the reach of experimental testing. That all changed in the 1960s with physicist John Stuart Bell. Bell devised a breathtakingly clever mathematical theorem that could, in principle, settle the argument once and for all. Bell's theorem provided a way to distinguish between the predictions of standard quantum mechanics and any local hidden variable theory. It set a specific statistical limit, now known as a Bell inequality, that any universe governed by local realism must obey. If experiments showed that this inequality was violated, then local hidden variables could be ruled out and spooky action would be a real feature of our world. The beauty of Bell's work was that it translated a metaphysical debate into a concrete, testable prediction. The subsequent decades became a race for experimental physicists to perform a definitive Bell test. The early experiments, led by pioneers like Elaine Aspect in the 1980s, were groundbreaking. They consistently showed violations of Bell's inequality, strongly supporting the quantum mechanical view. However, for years, a few potential loopholes remained. Skeptics could still argue that perhaps the particles were somehow communicating through some unknown but subliminal channel during the experiment. Or perhaps the detectors were inefficient and were only registering a biased sample of particles, creating the illusion of non-locality. Closing these loopholes required unprecedented levels of technological precision. The final decisive chapters in this story have been written in just the last several years. Multiple independent research groups around the world have now performed landmark, loophole-free Bell tests. These experiments used entangled particles separated by over a kilometer, with ultra-fast random measurement settings that were chosen after the particles had been emitted, ensuring no classical signal could possibly coordinate the results. The detectors were made so efficient that the fair sampling loophole was closed. The result, time and again, was a clear and decisive violation of Bell's inequality. The universe had voted, and it voted for spookiness. There are no local hidden variables. The connection between entangled particles is real, and it is non-local. So what does this mean for our understanding of reality? The experiments tell us what is not true, but they don't provide an easy picture of what is happening. One compelling interpretation is that the universe is not locally real. Realism in this context means that particles have definite properties, like a specific spin direction, even when we are not measuring them. The Bell test violation suggests that at the quantum level, this is simply not the case. The particles do not possess independent, predetermined states. Instead, their properties are undefined, existing in a haze of probability until the very moment a measurement is made, at which point the entire entangled system snaps into a specific configuration instantaneously. This doesn't allow for faster-than-light communication in the traditional sense. You can't use entanglement to send a message to another galaxy because the outcome of your measurement is still random. You can't control whether your coin lands on heads or tails. You can only know that the other coin has taken on the opposite value. It's a correlation without a causal signal, a shared existence that transcends spatial separation. This profound disconnect between the quantum world and the world of gravity and relativity represents the single greatest schism in modern physics. General relativity gives us a beautiful classical picture of a smooth, continuous space-time arena, where gravity is the curvature of that arena. Quantum mechanics gives us a bizarre, probabilistic picture of fields and particles that are fundamentally non-local. The two theories are mathematically and philosophically incompatible. The quest to reconcile them, to find a theory of quantum gravity, is the holy grail of theoretical physics. Approaches like string theory and loop quantum gravity are attempts to build a bridge across this chasm, to find a framework where the spooky, probabilistic connections of the quantum world can coexist with the smooth, geometric fabric of space-time described by Einstein. Entanglement itself is now seen not just as a bizarre curiosity, but as a potential cornerstone of this new understanding. Some theorists like Juan Maldacena and Leonard Susskind have even proposed a profound connection between entanglement and the very geometry of space-time through the ER equals EPR conjecture. This idea suggests that the spooky action at a distance, the EPR correlation, might be physically manifested as a tiny wormhole or Einstein-Rosen bridge connecting the entangled particles. In this breathtaking vision, the weirdest feature of quantum mechanics and the strangest feature of general relativity could be two different descriptions of the same underlying reality. Our journey through 25 unexplained anomalies from the pioneer drift to quantum spookiness reveals a universe that is not a clockwork mechanism of predictable laws, but a living, breathing, and deeply mysterious entity. Each of these puzzles, from the galactic to the subatomic, is a crack in the facade of our current understanding, a place where the light of a deeper truth shines through. There are not failures of science, but its very engine. There are the questions that keep us up at night, the cosmic challenges that force us to think bigger, dig deeper, and imagine the impossible. For in the end, it is the anomalies, the outliers, the data that doesn't fit, that truly propel us forward. They remind us that the universe is far stranger, far more wondrous, and far more beautiful than we have yet been able to conceive. And the greatest adventure lies not in the answers we have already found, but in the magnificent, unresolved mysteries that still await us. So where does this grand tour of cosmic glitches and terrestrial head-scratchers leave us? After examining 25 distinct anomalies, from spacecraft that defy orbital predictions to particles linked across the cosmos, a powerful, unifying theme emerges. Our current models of physics, while incredibly successful, are not the final word. There are approximations, brilliant but incomplete maps of a territory far stranger than we imagine. It's as if we've been expertly navigating the coastlines of a continent, only to now receive reports from the interior describing creatures and landscapes that our existing charts simply have no room for. These anomalies aren't random failures, they are systematic clues pointing toward deeper layers of reality that our current theories cannot yet describe. One of the most persistent themes running through these mysteries is the compelling, yet frustrating, evidence for a hidden cosmos operating just beyond our direct perception, the so-called dark sector. The inexplicable rotations of galaxies, the unexplained motion of galaxy clusters in dark flow, and the anomalous glow at our galactic center all whisper the same story. The universe is dominated by something we cannot see. Dark matter and dark energy are not just placeholders for our ignorance. They are active, dynamic components of the cosmos that seem to interact with the familiar world of atoms and light only through the faintest gravitational touch. The sheer diversity of these phenomena suggests this dark sector is not a single, simple substance. It might be a whole family of particles and forces, a parallel physics operating in the shadows, whose subtle influences are only now becoming apparent through their gravitational footprints on the visible universe. Equally profound is the recurring challenge to our understanding of gravity itself. Newton's laws and Einstein's general relativity have been the bedrock of cosmology for a century, but the pioneer and flyby anomalies, the flat galaxy rotation curves, and even the distribution of matter in the bullet cluster all apply pressure to this foundation. This has forced physicists to consider two radically different paths forward. The first is that we must discover new particles, WIMP actions, or something else entirely to account for the missing mass. The second, more revolutionary path is that our theory of gravity is itself flawed at certain scales. Modified Newtonian dynamics, or MEND, and its relativistic extensions represent a bold attempt to rewrite the rules of the cosmic dance without invoking invisible actors. The stalemate between these two approaches is one of the most significant in all of science, and its resolution will fundamentally reshape our concept of force, mass, and the fabric of space-time. Beyond the dark sector and gravity, a third theme points to the bizarre and counterintuitive world of quantum mechanics as a potential key to cosmic scale puzzles. The confirmed reality of quantum entanglement, with its spooky action at a distance, demonstrates that the universe is fundamentally non-local at a microscopic level. This profound interconnectedness challenges our very notions of space and separation. Could such quantum weirdness be manifesting on a grand scale? The GZK cutoff paradox, where ultra-high-energy cosmic rays appear to be the universal speed limit, might be hinting at a breakdown of Lorentz invariance, a slight modification of Einstein's relativity at the highest energies that could be a signature of a deeper quantum theory of gravity. The theoretical connection between entangled particles and microscopic wormholes, known as the ER equals EPR conjecture, is a breathtaking example of how the spookiness of the quantum world might be intimately woven into the geometry of space-time itself. Perhaps anomalies like the CMB cold spot are not just statistical flukes, but the macroscopic imprints of such quantum gravitational effects, or even collisions with other universes in a vast multiverse. Ultimately, what this collection of enigmas teaches us is that unexplained phenomena are not the end of science, but its most vital beginning. Every great revolution in human thought has been precipitated by an anomaly that refused to go away. The slight wobble in Mercury's orbit was a tiny crack in Newton's magnificent edifice, a crack that ultimately led Einstein to the profound insights of general relativity. The ultraviolet catastrophe in blackbody radiation was a paradox that classical physics couldn't solve, forcing Planck to invent the quantum and launch a century of discovery. Today we are surrounded by similar cracks and paradoxes: the Hubble tension, the lithium problem, the fast radio bursts. These are our generation's Mercury orbits and ultraviolet catastrophes. They are the universe's way of telling us that our current maps are insufficient, that there is a richer, more complex, and more astonishing reality waiting to be uncovered. This is the exhilarating frontier of modern physics. We are no longer just filling in the details of an established picture. We are standing at the edge of a new paradigm, gathering the clues that will lead us to a theory of quantum gravity, a complete understanding of the dark universe, and perhaps even an answer to the question of whether our cosmos is alone or part of an infinite multiverse. The journey to solve these anomalies will require new telescopes, new particle colliders, and new experiments, but more than that, it will demand new ideas, new mathematics, and a renewed willingness to question everything we think we know. The greatest discoveries lie not in the comfortable glow of established knowledge, but in the dark, uncharted territories illuminated by these 25 brilliant, puzzling, and utterly captivating anomalies. And so the pressing question becomes, how do we move forward? With such a dazzling array of cosmic puzzles laid out before us, the path to enlightenment is not one of passive waiting, but of active, ingenious pursuit. The next few decades are poised to be a golden age of discovery, powered by a new generation of telescopes, detectors, and experiments so advanced they seem almost like science fiction. These are the tools being forged right now to pry open the universe's deepest secrets, and they are targeting our greatest anomalies with breathtaking precision. At the forefront of this charge is the James Webb Space Telescope, an instrument that has already begun to fundamentally rewrite the story of the cosmos's first chapters. But its work is far from over. One of its primary missions is to directly observe the epoch of reionization, that pivotal era when the first starlight burned away the cosmic fog. By peering at the most distant quasars and the faint early galaxies around them, JWST is gathering the data to resolve the reionization timeline tension once and for all. It will determine whether those surprisingly bright, massive galaxies it discovered were indeed efficient enough to ionize the universe, or if their light was trapped by dust, forcing us to consider a more complex, drawn-out process involving countless fainter, unseen sources. Each new deep field image is not just a pretty picture, it is a core sample from the dawn of time, holding the chemical and physical clues to how our universe transitioned from a simple, dark expanse to the complex, luminous tapestry we see today. Beyond the realm of light, a completely new sense is opening up for humanity, the ability to hear the cosmos. Gravitational wave astronomy, born from the monumental detection of colliding black holes in 2015, is still in its infancy, but its potential is limitless. The upcoming Laser Interferometer Space Antenna, or LISA, will be a revolutionary space-based observatory designed to detect low-frequency gravitational waves that are completely inaccessible from Earth. While our current ground-based detectors like LIGO and Virgo listen to the violent chirps of stellar mass black holes and neutron stars, LISA will hear the deep, rumbling hum of supermassive black holes, merging at the hearts of distant galaxies. But its true potential for anomaly hunting lies in the exotic. Lisa could detect the faint, steady signal from a cosmic string, a hypothetical one-dimensional crack in space-time left over from the Big Bang vibrating as it stretches across the universe. It might even sense the background rumble from a first-order phase transition in the early universe, a colossal event where the fabric of space itself violently shifted state, potentially creating the very anomalies we see in the Simba today. This would be direct evidence for physics at energies a trillion times higher than any particle collider can reach, opening a window onto the universe's first fleeting moments. Meanwhile, back on Earth and deep underground, the hunt for dark matter is entering its most sensitive phase yet. For decades, the primary strategy has been to wait for a WIMP, a weakly interacting massive particle, to bump into the nucleus of an atom in a vat of ultra-pure material, shielded from cosmic rays in a mine or under a mountain. Experiments like LUX Zeppelin, Xeno NT, and Panda X are pushing the boundaries of sensitivity, creating environments so quiet that they could hear the proverbial pin drop in a cosmic hurricane. Yet the continued silence has prompted a dramatic shift in strategy. Physicists are now casting a much wider net, searching for a whole zoo of potential dark matter candidates. This includes the hunt for actions, incredibly light and wave-like particles, using powerful magnetic fields to convert them into detectable microwave photons in experiments like the Action Dark Matter experiment. There are even searches for dark matter that interacts so feebly that it passes through the entire Earth without a trace, requiring gigantic, novel detectors to have any hope of a discovery. And we cannot forget the particle colliders, which attempt to create dark matter in the laboratory. The Large Hadron Collider, which famously discovered the Higgs boson, is undergoing a major upgrade to dramatically increase its collision rate. By smashing protons together with unprecedented energy and frequency, it could potentially produce dark matter particles directly. While these particles would escape the detector unseen, their presence would be inferred by a telltale imbalance in the momentum of the collision products, a signature of missing energy carried away by the invisible matter. The LHC and its future successors are not just machines for finding new particles. They are tools for recreating the conditions of the early universe, allowing us to test whether the dark sector is populated by a single type of particle or a rich landscape of hidden particles with their own hidden forces, a concept known as the dark sector paradigm. The investigation extends even to our own solar system, where missions are being designed to test the very foundations of gravity. While the Pioneer anomaly was largely resolved, the flyby anomaly remains an open case. Future missions with even more precise tracking systems, perhaps using laser ranging from satellites to Earth, could measure a spacecraft's velocity during an Earth flyby with the accuracy needed to finally confirm or rule out the tiny, unexplained velocity jumps. Such a mission would serve as a direct test of general relativity in a new regime, potentially revealing subtle flaws or confirming exotic ideas like the rotational frame dragging effect. Furthermore, dedicated missions to the outer solar system, equipped with modern instrumentation, could perform a definitive survey of the Kuiper Cliff, searching for the hypothetical planet 9 or confirming that the drop-off in objects is indeed the primordial edge of our planetary disk. This grand multi-pronged investigative effort, spanning from the quantum to the cosmic, represents humanity's collective intellect at its most ambitious. We are no longer simply looking at the universe. We are listening to it, feeling for its vibrations, and trying to recreate its birth in our greatest machines. The coming years will not provide all the answers, but they will certainly deliver a torrent of new, high-quality data. Some anomalies will be resolved, likely in ways we cannot yet foresee, revealing our current models to be merely approximations. Others will deepen, becoming even more perplexing and forcing us to consider even more radical explanations. This is the thrilling, unpredictable nature of scientific progress. Each mystery solved opens the door to two new ones, and each new instrument we build extends our senses just a little further into the dark, teaching us not only about the universe, but about the limits of our own imagination and our unyielding drive to understand our place within this magnificent, mysterious cosmos. As we've journeyed across the cosmos from the gravitational whispers of the Pioneer anomaly to the spooky quantum links between entangled particles, one truth has become inescapably clear: Space-time is not the smooth, predictable stage we once imagined. It's a dynamic, sometimes chaotic fabric, riddled with glitches that defy our most established laws. Imagine the sheer audacity of a reality where entire galaxy clusters stream toward an unseen horizon in a dark flow, where ancient light from the Big Bang carries a mysterious cold spot possibly imprinted by collision with another universe, and where particles millions of light years apart decide their fates in perfect, instantaneous sync. These aren't minor puzzles, they are fundamental challenges, cosmic breadcrumbs leading us toward a far richer and more mysterious reality than our textbooks ever described. What's truly remarkable, however, isn't just the existence of these enigmas, but what they reveal about the scientific process itself. Far from being a sign of weakness, every unexplained anomaly is a testament to science's greatest strength, its relentless, self-correcting drive to question everything. Think of the Hubble tension, where our most precise measurements of the universe's expansion rate stubbornly refuse to agree. That isn't a failure, it's a glaring signpost pointing toward new physics, perhaps a dynamic form of dark energy, or even a flaw in our core cosmological model. Each mystery we've explored, from the missing lithium in the primordial universe to the bizarre thrust of the M drive, represents a frontier. They are the places where our current understanding ends and the next great discovery is waiting to begin. This is how science truly advances, not by clinging to comfortable ideas, but by courageously following the evidence, no matter how strange the path may become. So where do we go from here? The investigation is far from over. In many ways, it's just getting started. The next generation of tools, from the profound sensitivity of the James Webb Space Telescope peering into the era of the first galaxies, to the space-based gravitational wave observatory, LISA, listening for the ripples from cosmic strings, are already extending our senses into the unknown. Underground labs are hunting for dark matter with ever more ingenious traps, and particle colliders are recreating the universe's first moments in a quest to uncover hidden particles and forces. We're living in a golden age of cosmic detective work, and you have a front row seat. The story of these 25 anomalies is ultimately our story, a reflection of our insatiable curiosity and our humble acknowledgement that we're only beginning to comprehend the grand, mysterious tapestry of existence. Now we want to hear from you. Which of these cosmic head-scratchers keeps you up at night? Is it the haunting brevity of the wow, signaled a potential hello that was never repeated? The impossible geometry of Saturn's hexagon, a perfect shape etched into a roiling gas giant? Or does the confirmed spookiness of quantum entanglement fundamentally reshape how you think about reality itself? Share your thoughts and your favorite anomaly in the comments below. We read every single one, and the discussion among this community of cosmic explorers is one of the best parts of the journey. If you want to continue unraveling the universe's greatest mysteries with us, make sure to subscribe and hit the notification bell. We're just getting started, and the next cosmic revelation is always just